There's a gap in the story of Earth, a silence that spans millions of years. What if humans weren't the first technological civilization on this planet? This is the Silurian Hypothesis, a scientific question, not science fiction. Proposed by NASA researchers, it asks, if an advanced species lived on Earth long before us, would we even notice? Over millions of years, nearly all evidence disappears. Skyscrapers turn to dust. Plastics break down. Fossils? Rare. But some traces, like unusual carbon levels or rapid climate shifts, could remain buried in the geological record. And we've found them. Spikes of carbon. Layers of warming. Events with no clear cause. Coincidence? Maybe. Or the last echoes of a civilization erased by time. If it happened once, it could happen again. The Silurian Hypothesis presents a provocative challenge to the conventional understanding of human history by suggesting the possibility of advanced civilizations predating humanity's known origins. Coined by astrophysicist Adam Frank and planetary scientist Gavin Schmidt, the hypothesis asks us to consider whether Earth might have once harbored intelligent life forms whose technological footprints have since been erased by natural geological processes. Unlike traditional archaeological narratives that focus solely on human evolution, it invites scientists to explore the idea that civilization itself might be a recurring phenomenon across Earth's deep past. Fundamentally, the hypothesis questions the assumption that human civilization is unique or the first of its kind. It posits that evidence of ancient, technologically advanced societies could have been obliterated or hidden by natural events such as volcanic activity, tectonic shifts, erosion, or climate change. This possibility radically broadens the scope of archaeological inquiry, urging researchers to look for subtle, indirect signs such as anomalous isotopic signatures, unusual sediment layers, or inexplicable chemical residues that might indicate prior technological activity. The challenge lies in the fact that Earth's geological record is inherently incomplete and often ambiguous. Conventional archaeology relies heavily on artifacts, structures, and cultural remains, which are susceptible to destruction over millions of years. The Silurian Hypothesis, therefore, emphasizes a multidisciplinary approach, combining geology, climatology, and advanced scientific techniques like isotope analysis and computer modeling to search for subtle clues buried deep within Earth's strata. By framing the question of ancient civilizations in this way, the hypothesis not only stretches the boundaries of scientific inquiry, but also prompts us to reconsider the nature of civilization itself. It raises profound questions about the longevity of technological societies and their potential cycles of rise and fall. As we delve into this hypothesis, it becomes clear that understanding whether Earth once hosted pre-human civilizations could dramatically reshape our perspective on life's resilience, the history of intelligence, and the uniqueness, or universality, of human development. This leads naturally into the broader discussion of why contemplating ancient, pre-human civilizations holds such significance in scientific and archaeological research, a topic that will be explored next. The idea of ancient, pre-human civilizations holds profound significance for scientific and archaeological research because it prompts a re-evaluation of our understanding of human history and the broader narrative of planetary development. Traditionally, the archaeological record has been interpreted through the lens of a linear progression, from primitive societies to complex civilizations, culminating in the modern era. This perspective, however, rests on the assumption that humans alone are capable of creating advanced technological and cultural structures, and that any evidence of prior intelligent activity would be either non-existent or easily distinguishable from natural formations. Challenging this assumption broadens the scope of scientific inquiry. If civilizations existed before humans, their remnants could be obscured by time, geological processes, or even deliberate concealment. This makes the search for evidence more complex, but also more compelling, as it pushes researchers to develop innovative methods to detect subtle signs of past activity, such as anomalous isotopic signatures, unusual geological formations, or unexplained artifacts. Discovering such evidence would not only rewrite history, but also open new questions about the resilience and longevity of technological societies, their possible interactions with Earth's environment, and the factors that lead to their rise and fall. Furthermore, the significance of this idea extends into philosophical and existential realms. It challenges deeply embedded notions of human exceptionalism, that humanity is uniquely destined or distinguished in the universe. Recognizing the possibility of prior civilizations diminishes anthropocentric biases and encourages a more humble and expansive view of intelligent life's potential. It also invites interdisciplinary collaboration, integrating geology, astronomy, biology, and archaeology to construct a more holistic understanding of Earth's history. Ultimately, considering ancient pre-human civilizations underscores the importance of remaining open to scientific anomalies and remaining skeptical of assumptions that limit our view of the past. It encourages continuous refinement of investigative techniques and theoretical frameworks, ensuring that our pursuit of knowledge remains dynamic and receptive to revolutionary discoveries. This exploration not only deepens our comprehension of Earth's history, but also fosters a broader reflection on the nature of intelligence and civilization in the universe. The concept of human uniqueness has deep roots in both scientific inquiry and cultural worldview. Historically, this notion was shaped by the rapid development of scientific methods in the Renaissance and Enlightenment periods, which emphasized empirical observation and rationality. As scientific understanding advanced, humans have often been positioned at the center of the universe, an idea reinforced by the geocentric model and later by anthropocentric perspectives that placed humanity as the pinnacle of biological and cultural evolution. This anthropocentrism was further solidified by the observable complexity of human societies, language, and technological achievement, which seemed to set humans apart from other species, and, by extension, from any potential extraterrestrial or non-human civilizations. Underlying these assumptions were several key beliefs. One was that complexity and technological progress indicated a higher level of intelligence, leading to the idea that humans had achieved a unique evolutionary milestone. Another was the notion of divine or special creation, which positioned humans as deliberately placed at the universe's center or as distinct from the natural world. These ideas fostered a view that other civilizations, if they existed, would be fundamentally different or inferior, and perhaps unlikely to have arisen in the same manner as human civilization. Additionally, the scarcity of evidence for advanced non-human societies reinforced the perception of human exceptionalism. Historically, our limited understanding of ancient civilizations and the lack of detectable extraterrestrial signals created a presumption that humanity was alone, or at least the first intelligent species to emerge. This assumption was also influenced by the difficulty of detecting subtle signs of non-human civilization activity across cosmic distances, leading to a bias toward believing in human uniqueness. However, this perspective has been challenged by developments in astrobiology, archaeology, and the philosophy of science. The recognition that Earth's history might include prior, technologically capable civilizations, potentially long before humans, forces us to re-evaluate deeply ingrained assumptions about what constitutes intelligence and progress. It invites us to question whether our criteria for civilization are too narrow and whether the universe might host a diversity of intelligent life forms, each with their own trajectories, independent of human standards. This re-evaluation lays the groundwork for exploring broader scientific and philosophical implications of non-human civilizations predating humanity. Contemplating the existence of non-human civilizations predating humanity carries profound scientific and philosophical implications that challenge long-held assumptions about our place in Earth's history. Scientifically, it pushes researchers to refine methods of detecting and interpreting geological and biological records. If ancient civilizations existed long before humans, then current stratigraphic techniques and radiometric dating methods may need to be reassessed to account for potential overlooked signals or anomalies indicative of technological activity. This invites a re-evaluation of the fossil record, sediment layers, and isotopic compositions for signs of artificial structures or materials which could be subtle or misinterpreted as natural phenomena. It also raises questions about the resilience and durability of technological artifacts over millions of years. Could remnants of such civilizations be buried deep or eroded away, eluding detection? Philosophically, the notion that Earth may have hosted advanced civilizations prior to us fundamentally alters our understanding of progress, intelligence, and the uniqueness of human life. It challenges anthropocentric views that place humans at the pinnacle of evolutionary achievement, suggesting instead that intelligence and technological prowess might be recurring themes in planetary histories. This perspective fosters humility and encourages a broader view of life's potential trajectories, emphasizing that civilizations could rise and fall multiple times, perhaps leaving only faint traces behind. It also prompts reflection on the nature of consciousness and civilization itself. Are technological civilizations inevitable given certain planetary conditions? Or are they rare and transient phenomena? Furthermore, considering pre-human civilizations introduces complex questions about the longevity and impact of technological activity. Would such civilizations have interacted with their environments in ways that significantly altered planetary systems, and could these alterations be detectable today? These inquiries challenge our understanding of planetary resilience and the potential for cycles of rise and fall in technological advancement. As these scientific and philosophical implications unfold, they set the stage for examining how these ideas align or conflict with contemporary debates about extraterrestrial life and ancient advanced civilizations. The question of ancient, non-human civilizations on Earth intimately relates to broader discussions about whether similar or even more advanced societies might exist elsewhere in the universe. This connection underscores the importance of the Silurian hypothesis as a conceptual bridge between Earth's deep past and the search for extraterrestrial intelligence, prompting us to reconsider what constitutes evidence of civilization itself. The Silurian hypothesis, by positing the possible existence of advanced civilizations predating human history, naturally intersects with contemporary debates about extraterrestrial life and ancient advanced civilizations. At its core, the hypothesis challenges the conventional timeline of human development, suggesting that Earth's history may be far more complex than traditionally thought. This, in turn, opens the door to considering whether extraterrestrial intelligences may have influenced or even seeded early life on Earth, or whether ancient civilizations could have risen to technological heights long before recorded history. In the realm of extraterrestrial life, the hypothesis fuels speculation that Earth might not be an isolated cradle of intelligent life. The search for signs of ancient alien contact, such as anomalous artifacts or unexplained structures, gains renewed significance within this framework. If ancient civilizations existed prior to humans, perhaps their origins or sudden technological leaps were influenced by extraterrestrial encounters, or perhaps their remnants have been misinterpreted as myth or natural formations. The hypothesis invites scientists and researchers to reconsider the origins of certain archaeological mysteries, pondering whether some artifacts or geological anomalies could be remnants of pre-human civilizations or extraterrestrial interventions. Furthermore, the Silurian hypothesis echoes the long-standing fascination with ancient civilizations that supposedly possessed advanced knowledge or technology, like Atlantis, Lemuria, or other mythic lands. These stories, often dismissed as myth, could be viewed through a new lens. Perhaps they encode collective memories of real events involving civilizations that predates recorded history. The hypothesis challenges us to evaluate whether these myths are symbolic or literal, and whether they might hint at suppressed or forgotten chapters of human or non-human history. This intersection also prompts a re-evaluation of how history and myth intertwine. While mainstream science tends to view such narratives skeptically, the hypothesis encourages an open-minded approach to examining the archaeological and geological record for clues of earlier, possibly non-human, civilizations. With ongoing advancements in archaeology, astrobiology, and planetary sciences, the boundaries between myth, history, and scientific discovery become increasingly blurred, fostering an intriguing dialogue about the true age and origins of civilization on Earth, and perhaps beyond. Throughout history, numerous mythological and historical narratives have both supported and challenged the idea that advanced civilizations might have existed long before humans. Some ancient cultures, for instance, recount stories of lost worlds and primordial beings that seem to hint at a distant, more advanced past. The Sumerians, often regarded as one of the earliest known civilizations, believed their society was a gift from divine beings who descended from the heavens, implying an origin story that may hint at a much older, pre-human history. Similarly, the ancient Egyptians held mythologies describing their land as the site of a primordial chaos, which was then ordered by gods, suggesting a conception of history that predates recorded human civilization. In contrast, many traditional narratives explicitly place human civilization as the starting point of history, emphasizing the idea of progress from primitive origins. These stories challenge the notion of prior civilizations by framing human development as a linear, unbroken trajectory starting from a supposed beginning. Such perspectives are reinforced by religious texts that often describe a divine creation event as the origin of humanity, implicitly dismissing the possibility of earlier intelligent life or civilizations. However, some legends and archaeological findings have been interpreted as potential evidence for ancient advanced societies predating known history. For example, tales of Atlantis, described by Plato, depict a highly developed civilization that vanished beneath the sea, sparking debates about whether such stories could have a basis in historical reality or serve as allegories. Similarly, certain megalithic structures, such as the Great Pyramids or Stonehenge, have prompted speculation about the technological capabilities of ancient builders, fueling hypotheses about lost knowledge or civilizations. Despite these narratives, mainstream science remains cautious. They typically regard myth as symbolic or allegorical rather than literal histories. The challenge, then, is determining whether such stories encode collective memories of real events or are purely imaginative constructs. To move beyond speculation, scientific inquiry must examine physical evidence, an endeavor that requires rigorous testing and verification. This sets the stage for exploring how scientific methods like geology, paleontology, and archaeology can critically evaluate the plausibility of ancient civilizations predating humans. Scientific disciplines, such as geology, paleontology, and archaeology, are integral to rigorously testing the Silurian hypothesis, each offering unique insights into Earth's deep history. Geology provides the foundational framework by analyzing rock formations, stratigraphy, and mineral compositions. Through precise dating techniques like radiometric dating of volcanic ash layers or isotopic analysis, geologists can establish timelines that extend far beyond recorded human history. If anomalies or unexpected features are identified within ancient strata, such as unusual mineral deposits, large-scale disturbances, or signs of prior thermal events, they could serve as indirect evidence of past advanced civilizations. Paleontology complements this approach by examining fossils preserved within these geological layers. While traditionally focused on biological evolution, paleontologists also look for anomalies, such as sudden shifts in fossil assemblages or inexplicable artifacts embedded within sediment layers that might suggest prior technological activity or environmental disruptions not attributable to known natural processes. For instance, unusual microstructures or materials resembling manufactured objects could indicate prior technological civilizations. Archaeology, though often associated with recent human activity, extends its investigative scope through the study of anomalous artifacts and bioarchaeological evidence in ancient deposits. Advanced analytical techniques, such as spectroscopy, electron microscopy, and chemical residue analysis, allow scientists to distinguish between natural mineral formations and potentially manufactured materials. Detecting anomalous metals, alloys, or synthetic compounds in ancient sediments could suggest previous industrial activity, prompting further scrutiny. Together, these disciplines form a multidisciplinary approach that critically evaluates the stratigraphic record for signs of prior civilizations. By integrating geological timelines with fossil and artifact analyses, researchers aim to identify inconsistencies or unexplained phenomena that challenge current assumptions about Earth's history. The robustness of this scientific methodology ensures that any claims regarding ancient, undiscovered civilizations are supported by converging lines of evidence. As we consider the implications of potential findings, it's essential to recognize that this rigorous scientific process is designed to differentiate between natural processes and extraordinary hypotheses. Should evidence emerge supporting the Silurian hypothesis, it would necessitate a profound re-evaluation of what we understand about the evolution of life, technological development, and the resilience or vulnerability of planetary ecosystems over geological timescales. If the Silurian hypothesis were validated, revealing that an advanced civilization once thrived on Earth long before humans, it would fundamentally alter our understanding of planetary and biological history. Currently, the prevailing view positions humans as the pinnacle of evolution, with technological development as a recent and unique phenomenon. Confirming an ancient, technologically capable civilization would challenge this anthropocentric perspective, suggesting that intelligence and technological capability are not exclusive to our species or recent in Earth's timeline. This realization could imply that complex life forms with advanced societies have arisen multiple times, perhaps driven by the same evolutionary pressures, but with their own distinct trajectories. Such a discovery would also prompt a re-evaluation of the resilience and vulnerability of planetary environments. If a prior civilization significantly altered Earth's geology through large-scale mining, construction, or environmental manipulation, that would necessitate a reassessment of the planet's natural resilience and capacity for recovery. It would raise profound questions about the longevity of technological societies and whether planetary conditions favor their long-term survival or inevitably lead to their demise. This, in turn, could influence theories about the sustainability of our current civilization, emphasizing the importance of understanding and mitigating long-term planetary impacts. Moreover, the hypothesis's validation would compel scientists to revisit the timeline of Earth's habitability. It might indicate that planetary conditions conducive to life and civilization are more common than previously believed, or conversely, that such conditions are fleeting and punctuated by catastrophic events that reset the evolutionary clock. This layered history would add complexity to models of Earth's climate evolution, biosphere resilience, and the potential for life elsewhere in the universe. Ultimately, confirming the existence of a prior civilization would deepen our appreciation of Earth's intricate history, emphasizing that our planet's story is not solely a linear progression, but a mosaic of civilizations rising, falling, and leaving indelible marks. Recognizing these ancient signatures would open new avenues of inquiry, forcing us to consider not just what life is, but what it can achieve, and what remnants it leaves behind. This profound shift in perspective would redefine our understanding of planetary evolution, encouraging us to look more carefully for traces of civilizations long gone. Identifying the footprints of a prior advanced civilization within the geological record requires discerning subtle yet telling signatures embedded deep within Earth's layered history. Unlike the more conspicuous artifacts of recent plate, cryomed humans, ancient technological activities leave behind indirect but measurable clues can be uncovered. Meticulous analysis of geological signatures. These signatures may manifest in various forms, each providing a different window into past civilizations' environmental impact and technological prowess. One of the key indicators is abnormal sedimentation patterns. Civilizational activity, such as large-scale construction, resource extraction, or land modification, can significantly alter sediment deposition. For example, anomalously thick or compositionally distinct layers within sedimentary sequences may suggest episodes of intensive material processing or habitat modification. These layers often contain unusual concentrations of processed minerals or synthetic materials that would be unlikely to form naturally, such as specific metal alloys or industrial byproducts. Isotopic anomalies represent another vital clue. Technologically advanced civilizations might have introduced alterations in natural isotopic ratios through activities like smelting, alloying, or chemical processing. For instance, shifts in the ratios of isotopes of elements like lead, copper, or iron beyond natural fluctuations could indicate large-scale industrial activity. Such anomalies, preserved in mineral deposits or sediments, serve as chemical fingerprints of technology-driven environmental alteration. Mineral deposits themselves can be revealing. Certain mineralogical features, such as synthetic compounds, unusual crystal structures, or metals concentrated in ways inconsistent with natural processes, may hint at deliberate technological intervention. For example, the presence of high-temperature mineral phases or residues of synthetic materials like early ceramics or metallurgical slags embedded in ancient sediments would strongly suggest prior technological activity. Understanding these signatures depends on recognizing that human or alien technological influence often leaves behind a layered chemical and mineralogical legacy. These clues, carefully interpreted, could offer compelling evidence that an advanced civilization predated our own, subtly woven into the Earth's geological fabric. As we delve deeper into these signatures, the question naturally arises: how can sediment layers, isotopic anomalies, and mineral deposits serve as clues to ancient technological activity? Sediment layers, isotopic anomalies, and mineral deposits serve as crucial indicators in the quest to uncover evidence of ancient technological activity, offering subtle yet compelling clues embedded within Earth's geological record. These features, when meticulously analyzed, can reveal patterns that diverge from typical natural processes, hinting at past interventions by intelligent beings. Sediment layers often form through the gradual accumulation of particles over time, but anomalies such as unusually thick or disturbed strata can suggest episodes of rapid deposition or mechanical disruption. For instance, layers exhibiting signs of thermal alteration, unusual compaction, or anomalous grain sorting may point toward activities like mining, construction, or artifact deposition. In some cases, sediment disruptions align with known technological operations, such as the presence of crushed rock fragments or artificial conglomerates interwoven with natural sediments. Isotopic anomalies provide another vital clue. Variations in isotopic ratios, such as shifts in carbon, nitrogen, or specific metal isotopes, may reflect processes beyond natural cycles. For example, a sudden spike in certain isotopes could indicate the presence of high-temperature processing or metallurgical activities. These anomalies often stand out from natural baseline signatures, especially when correlated with other geological features, suggesting potential human or extraterrestrial technological interventions. Mineral deposits further bolster evidence when they display unusual compositions or formation patterns. For instance, the presence of synthetic-looking mineral phases, such as artificially produced ceramics or metal oxides, can be detected through advanced mineralogical analysis. Additionally, mineral deposits resulting from industrial processes, like slag or fused silica, may be found embedded within geological strata, serving as direct markers of ancient manufacturing. Collectively, these geological clues, sediment anomalies, isotopic deviations, and distinctive mineral deposits can construct a compelling narrative of ancient technological activity. Yet, interpreting them requires careful, multidisciplinary analysis to distinguish between natural variability and signs of past civilizations. This naturally leads to a deeper inquiry into the subtle and often ambiguous challenge of differentiating natural geological phenomena from artifacts of ancient engineering, a topic that continues to intrigue researchers and challenge established paradigms. Distinguishing natural geological processes from artifacts of ancient civilizations presents a complex and nuanced challenge for researchers investigating Earth's deep past. Over millions of years, Earth's surface has been sculpted by an array of dynamic phenomena: volcanic eruptions, tectonic shifts, erosion, sedimentation, and mineralization, all of which can produce formations that mimic or obscure evidence of human activity. Without contextual data, these features risk being misclassified as natural formations. Conversely, actual artifacts may be heavily eroded, chemically altered, or buried deep within the geological strata, making their identification challenging even with advanced imaging techniques. The process of differentiating genuine signs of past civilizations from natural processes demands meticulous stratigraphic analysis, high-resolution imaging, and often interdisciplinary approaches, combining geology, archaeology, and geochemistry. Furthermore, Earth's geological history is marked by catastrophic events, such as massive volcanic eruptions, meteorite impacts, and rapid climate shifts that can both destroy evidence of ancient civilizations and create confusing geological signatures. For instance, a volcanic ash layer might overlay a site presumed to be archaeological, making it difficult to determine whether an artifact predates or postdates the event. Similarly, mineralization processes can produce features that resemble man-made modifications, yet they are purely natural. Advances in technology have improved our ability to distinguish these phenomena, yet the challenge remains significant. Techniques like isotopic dating, remote sensing, and geophysical surveys help differentiate between natural and anthropogenic origins, but interpretations often require cautious skepticism and corroborative evidence. As our understanding deepens, the line between natural geological features and potential signs of ancient civilizations continues to be refined, setting the stage for exploring how planetary events, such as impact craters, might preserve evidence of civilizations long lost to time. Impact craters and planetary events serve as natural archives of Earth's tumultuous history, potentially offering clues to ancient civilizations long vanished. When a massive asteroid or comet strikes the planet, the resulting crater becomes a durable record of catastrophic events. These impact sites often contain layers of melted rock, shocked minerals, and ejecta deposits that can be radiometrically dated to pinpoint the timing of the impact. If such an event coincided with a period of advanced technological activity, it might have left behind subtle yet detectable traces, such as anomalous material compositions or unusual mineral formations that could suggest a civilization's existence at that time. Furthermore, planetary events like large-scale volcanic eruptions or seismic upheavals could also impact the preservation of cultural artifacts. For instance, widespread ash layers from supervolcanoes create stratigraphic markers that can be correlated across regions. If an ancient civilization existed during or prior to these events, their remnants, be it tools, architectural fragments, or even bioindicators, might be buried beneath these ash layers. Over millennia, such deposits could be preserved within the stratigraphy, effectively sealing evidence of early technological prowess beneath layers of geological activity. Impact events and planetary upheavals also influence climate and environmental conditions, which can affect the preservation potential of organic and inorganic materials. Sudden climate shifts may either accelerate decay or, conversely, promote exceptional preservation in certain environments. For example, the intense heat and pressure from impacts could produce unique mineralogical signatures. These signatures, if found in conjunction with other geological anomalies, might serve as indirect evidence of civilization, especially if they correlate with other archaeological indicators. As we consider the deep time record, the importance of these planetary events becomes even clearer. They act as both destructive forces and preservers of history, capturing snapshots of Earth's past that might include signs of civilizations predating our current understanding. This raises a compelling question. What role do deep-sea sediments and ice cores play in uncovering evidence of ancient technological activity? These natural archives may hold the key to revealing secrets buried within Earth's geological record, offering a window into civilizations lost to time. Deep-sea sediments and ice cores serve as invaluable archives of Earth's environmental history, offering unique insights into periods predating known civilizations and potential signs of ancient technological activity. These natural repositories preserve a layered record of atmospheric, oceanic, and terrestrial conditions over hundreds of thousands to millions of years, making them essential tools for investigating the possibility of earlier advanced societies. Deep-sea sediments accumulate gradually on ocean floors, capturing a complex mixture of mineral particles, organic matter, and microfossils. Within these deposits, researchers can identify anomalous chemical signatures, unusual mineral formations, or traces of rare elements that may indicate technological processes such as metallurgy, alloy production, or even chemical engineering by ancient civilizations. For instance, elevated concentrations of metals like gold, platinum, or rare earth elements, beyond what would be expected from natural geochemical cycles, could suggest mining or metallurgical activity that predates known civilizations. Similarly, ice cores extracted from polar regions preserve a chronological record of atmospheric composition, volcanic eruptions, and particulate matter. These cores contain layers of ash, soot, and chemical residues that can be meticulously analyzed for traces of industrial pollutants or technological byproducts. The presence of synthetic compounds, such as certain chlorofluorocarbons or other man-made chemicals, in layers dating far before modern industrialization could imply the existence of unknown, ancient technological processes capable of producing these substances. Furthermore, advanced analytical techniques, such as mass spectrometry, isotope ratio analysis, and synchrotron radiation spectroscopy, enable scientists to detect and quantify minute traces of materials within these complex matrices. These methods can distinguish between natural mineral signatures and those altered or introduced by technological activity. For example, isotopic anomalies in sediments or ice layers can reveal specialized manufacturing or resource extraction that would otherwise remain hidden. As a result, deep-sea sediments and ice cores stand at the forefront of uncovering subtle, yet potentially groundbreaking evidence of ancient technological activity. Their detailed stratigraphy and chemical records provide a chronological framework that, when interpreted with modern analytical tools, may illuminate the existence of civilizations long lost to time. Building upon this foundation, the next question explores how cutting-edge geochronology techniques can help date these elusive artifacts and signatures, further advancing our understanding of Earth's mysterious past. Modern geochronology techniques play a pivotal role in uncovering the deep history of Earth's surface, providing the temporal framework necessary to identify potential signatures of ancient, non-human civilizations. These methods allow scientists to precisely date geological formations, mineral deposits, and even subtle alterations in the Earth's crust that could harbor evidence of past technological activity or societal influence. One of the most widely used techniques is radiometric dating, which measures the decay of unstable isotopes within rocks and minerals. For example, uranium lead dating enables scientists to accurately determine the age of zircon crystals in ancient volcanic ash layers, establishing a chronological baseline that can be correlated with other geological features. When anomalies, such as unusual concentrations of certain elements or mineral structures, are detected within these layers, geochronology can help assess whether they might be the result of artificial activity, perhaps from a civilization predating humans. Additionally, techniques like argon-argon dating allow for the precise dating of volcanic eruptions and associated ash deposits, which often serve as chronological markers. This can be crucial in contextualizing potential artifacts or anomalous features within a well-defined temporal framework. Furthermore, advances in thermochronology, methods that measure the cooling ages of rocks, offer insights into tectonic events that might have exposed or buried ancient structures, providing clues about when and how such features could have been preserved or destroyed. Beyond radiometric methods, recent developments in isotope geochemistry, such as analyzing stable isotopic ratios, can reveal past environmental conditions potentially altered by technological activity. For instance, shifts in carbon or oxygen isotopic compositions might indicate large-scale environmental modifications consistent with industrial activity. However, while these tools are powerful, their application must be nuanced. The ability to date specific artifacts or signatures depends heavily on the preservation of physical evidence and the context in which they are found. As we probe deeper into Earth's ancient record, understanding the strengths and limitations of geochronology becomes essential in distinguishing genuine signs of pre-human civilizations from natural geological processes. This naturally leads to questions about the current boundaries of our geological detection methods and their capacity to reveal the most elusive traces of an ancient, possibly technologically advanced, civilization. While geological methods have revolutionized our understanding of Earth's deep past, they inherently possess certain limitations when it comes to detecting evidence of pre-human civilizations. These constraints stem from both the nature of geological processes and the scale at which they operate, making the task of uncovering ancient, potentially civilization-related signatures particularly challenging. One primary limitation is the vast timescale involved. Many early civilizations, if they existed, would have left behind subtle or transient markers that are easily overwritten or obscured over millions of years. Geological processes such as erosion, sedimentation, plate tectonics, and volcanic activity continually reshape the Earth's surface. These dynamic forces can erase or dilute traces of ancient human activity, especially when such traces are not robust or widespread. For example, a civilization that built primarily with perishable materials or left limited durable artifacts would leave minimal detectable evidence after extensive geological transformations. Furthermore, current geochronological techniques often have resolution thresholds that restrict their ability to pinpoint events or structures dating back hundreds of thousands or millions of years. Radiometric dating, isotope analysis, and stratigraphic methods are highly effective within certain timeframes, but become less precise or less applicable for very ancient deposits. This creates a blind spot for early civilizations that might have existed in epochs where geological signatures are faint or indistinct. Another significant challenge involves the identification of indirect or indirect evidence. Many potential traces, such as artificial modifications in mineral deposits, altered sediment compositions, or unusual isotopic ratios, may be subtle or ambiguous. Distinguishing these from natural geological phenomena requires a high degree of interpretative nuance, and sometimes such signals can be dismissed as natural anomalies or overlooked entirely. Lastly, the preservation bias plays a crucial role. Certain environments favor the preservation of evidence, like dry caves or stable mineral deposits, while others rapidly degrade or obliterate artifacts. These biases limit our ability to detect early civilizations that might have thrived in less favorable conditions. As a result of these constraints, our current geological toolkit, while powerful, offers an incomplete picture of Earth's distant past. This opens intriguing possibilities. Could some evidence of ancient civilizations have been erased or obscured by natural processes, or even more dramatically, by extraterrestrial impacts or cosmic events? Extraterrestrial impacts and cosmic events have long fascinated scientists and theorists alike for their potential to dramatically alter planetary histories. Such cataclysmic phenomena, including asteroid strikes, cometary impacts, and intense solar activity, are capable of causing widespread destruction that could obscure or eradicate evidence of even the most advanced ancient civilizations. When considering Earth's deep past, these events serve as powerful erase buttons capable of destroying surface structures, contaminating archaeological sites, and resetting the environmental conditions necessary for civilizations to thrive. One of the most compelling examples is the asteroid impact responsible for the Cretaceous-Paleogene extinction event approximately 66 million years ago. While this event led to the extinction of the dinosaurs, it also dramatically reshaped the planet's surface and biosphere. Such impacts leave behind distinctive geological signatures, iridium layers, shocked quartz, and crater formations that can be identified long after the event. However, if ancient civilizations existed prior to such impacts, their remnants could have been buried beneath vast layers of debris, eroded over eons, or transformed into metamorphic rocks, rendering them virtually invisible. Furthermore, cosmic phenomena like supernovae or gamma-ray bursts could have had profound effects on Earth's atmosphere and climate, leading to prolonged periods of environmental stress. These events could diminish or destroy the biological and technological artifacts that might hint at prior civilizations. The intense radiation and atmospheric changes might also accelerate erosion and sedimentation processes, effectively erasing surface evidence of any past societies. It is also worth considering that cosmic impacts could catalyze secondary effects, such as volcanic eruptions or climate shifts, that further obscure or destroy traces of ancient civilizations. These secondary effects could complicate the task of archaeologists and geologists seeking to uncover Earth's deep history. In this context, the role of extraterrestrial impacts in potentially erasing evidence of prior civilizations underscores the importance of examining the geological record with a nuanced perspective. While such catastrophic events can obscure the footprints of ancient societies, they also leave behind distinctive signatures that, if properly interpreted, can reveal invaluable insights into Earth's tumultuous past. This understanding naturally leads to the next intriguing question. How do fossils inform us about the possibility of ancient, non-human civilizations? Fossils serve as invaluable archives of Earth's deep past, offering glimpses into the evolution and diversity of life forms that once inhabited our planet. While traditionally interpreted as evidence of biological organisms, certain fossil anomalies and unusual structures challenge this conventional perspective and provoke consideration of alternative origins, including the possibility of ancient non-human civilizations or technological activity. One intriguing category of fossils involves anomalous mineral formations or microstructures that defy easy biological explanation. For example, some researchers have identified fossilized structures with intricate geometric patterns or symmetrical arrangements, features that are rare or absent in natural biological processes. These include complex fractal-like microstructures embedded within mineral matrices, which resemble machine-made or engineered components rather than naturally occurring biological tissues. Additionally, unusual carbonaceous or metallic inclusions within sedimentary layers sometimes display features reminiscent of manufactured devices or tools, such as regularized surfaces, layered composites, or microassembly. These anomalies could suggest past technological activity, especially if they exhibit characteristics incompatible with known biological fossilization processes. For instance, the presence of microstructures with precise, machine-like geometries, such as fine grooves, ridges, or apertures, raises questions about their origin, particularly if found alongside typical biological fossils. Another promising avenue involves the detection of isotopic or mineralogical anomalies that cannot be easily explained by natural geological processes alone. Such anomalies might include unusual elemental compositions, alloyed metals, or thermally altered materials inconsistent with known biological decay or mineralization pathways. These features could be indicative of artificial fabrication or technological intervention, especially if they are spatially associated with other anomalous structures. Moreover, the discovery of what some interpret as artificial markings, geometric engravings, or deliberate modifications on fossilized bones or shells invites speculation about ancient craftsmanship or machinery. When these markings are highly regular and patterned, they challenge the notion of purely biological origin and open the possibility of intentional design. In sum, while most fossils straightforwardly document biological evolution, Certain anomalies and unusual structures beckon us to consider a wider spectrum of origins, possibly even technological or artificial, prompting us to re-examine our assumptions about Earth's ancient past and the potential for distant, now extinct civilizations. Identifying fossil anomalies or unusual structures that might suggest technological activity or artificial origins involves a keen eye for deviations from natural biological processes. Traditional fossils primarily reflect biological morphology, shells, bones, or plant impressions. Yet certain anomalies could hint at the intervention of intelligent design or technology. For instance, irregular mineral deposits or formations that resemble manufactured components, such as symmetrical geometric patterns, microstructures mimicking circuit-like arrangements, or repetitive motifs, may signal artificial fabrication. These structures could include microfractures aligned with specific geometries, unusual alloy-like mineralization, or mineralized traces that resemble microcircuitry, all of which defy purely natural explanations. One promising line of inquiry involves examining mineralized tissues or matrices for signs of nanostructural engineering. For example, the presence of unusually uniform, layered deposits within fossilized tissues might suggest processes akin to nanofabrication. Similarly, the discovery of materials with properties inconsistent with known biological mineralization, such as metals or alloys embedded in fossils, could indicate technological manipulation. These anomalies might appear as embedded microelectronic components or synthetic composites preserved within ancient biological materials, especially if they display characteristics such as precise alignment or symmetry that surpass natural mineral growth. Another avenue lies in scrutinizing fossilized biofilms or microbial mats for signs of artificial structuring. If such structures exhibit complex organization, symmetry, or layered arrangements that are unlikely to result from natural microbial processes alone, they could hint at bioengineering. Additionally, unusual isotopic ratios or elemental compositions within these anomalies might suggest the introduction of non-biological materials, further supporting the hypothesis of technological involvement. The challenge remains in distinguishing genuine anomalies from natural variability or diagenetic effects, alterations during fossilization. Nonetheless, employing advanced imaging techniques such as electron microscopy, synchrotron radiation analysis, and spectroscopic methods can reveal minute details that escape conventional observation. These tools enable scientists to detect micro and nanoscale features that, if convincingly inconsistent with natural processes, could provide compelling evidence for ancient technological activity. This exploration naturally leads to a broader question. Can the study of microfossils reveal evidence of advanced biological or technological processes? The study of microfossils offers a powerful window into Earth's ancient biological history, providing critical clues about the origins and evolution of life. These tiny preserved remains, often less than a micrometer in size, can be extracted from rocks thousands to billions of old, revealing presence of primitive organisms long before the emergence of complex multicellular life. While traditionally associated with identifying simple microbial life, recent advances suggest that microfossils might also encode subtle signatures of biological complexity, potentially hinting at advanced processes. One intriguing avenue of research involves searching for morphological features within microfossils that suggest cellular differentiation, specialized structures, or metabolic pathways. For example, certain filamentous or spherical microfossils exhibit patterns of organization that resemble primitive biofilms or early forms of cellular cooperation. These features could imply that early microbes had already developed some degree of structural or functional complexity, perhaps even rudimentary forms of communication or resource sharing, traits that could be seen as precursors to more advanced biological systems. Furthermore, chemical analyses of microfossil inclusions can reveal isotopic signatures indicative of metabolic activities that surpass simple energy processing. For instance, specific ratios of carbon or sulfur isotopes might suggest the existence of metabolic pathways akin to those found in modern extremophiles or even early forms of photosynthesis. Such findings could challenge the notion that early life was solely simplistic, hinting instead at a spectrum of biological sophistication that may include processes now associated with advanced organisms. Beyond biological processes, some microfossil structures have been hypothesized to encode evidence of technological interactions, such as mineralization patterns or unusual elemental compositions that could imply biological manipulation of their environment. While these interpretations remain contentious, they underscore the potential for microfossils to harbor subtle clues about the possible coexistence of biological and technological phenomena in Earth's deep past. Overall, the investigation of microfossils extends our understanding of life's evolutionary trajectory, suggesting that the earliest life forms may have possessed more complexity than traditionally assumed. This raises provocative questions about the nature of biological innovation and whether early microbes could have harbored processes or capabilities that challenge our current evolutionary models. Such insights compel us to consider how ancient microbial life or complex fossils might fundamentally reshape our understanding of the development of life on Earth and perhaps the potential for advanced life elsewhere. The discovery of ancient microbial life or complex fossils significantly enriches our understanding of biological evolution, but it also introduces complex challenges in interpretation. Microbial fossils, often preserved as minute mineralized filaments or stromatolites, serve as some of the earliest evidence of life on Earth. These tiny structures push back the timeline of biological activity, revealing that life's origins may date to over 3.5 billion years ago. However, their microscopic size and simple morphology make it difficult to distinguish genuine biological signatures from abiotic mineral formations that can mimic biological patterns. For instance, certain mineral precipitates can produce filamentous or layered structures that resemble microbial colonies, complicating efforts to confirm their biogenic origin. Similarly, the discovery of more complex fossils, such as soft-bodied organisms or early multicellular forms, can challenge traditional evolutionary models. Fossils with intricate features may suggest a higher level of biological sophistication at earlier periods than previously thought. Yet, their interpretation is often complicated by taphonomic processes, the ways in which organisms decay and are preserved, which can distort or obscure original biological features. This raises questions about whether some fossils genuinely represent ancient life or are the result of mineral replacements or other natural geological processes. Furthermore, the stratigraphic context of these fossils plays a crucial role. The layering of sediments can sometimes be misleading, with mineral deposits migrating or forming in ways that produce structures resembling biological entities. These natural mineralizations, often induced by geological activity, can produce intricate patterns that superficially appear biological but are purely mineral in origin. Crucially, researchers must apply rigorous analytical techniques such as isotopic analysis, microscopy, and chemical characterization to differentiate truly biological fossils from abiotic artifacts. These methods help identify biosignatures, like specific isotopic ratios or organic molecules, that are indicative of life. Nonetheless, the potential for false positives remains, especially when dealing with ancient, heavily altered specimens. Consequently, the line between natural mineral formations and genuine evidence of ancient life is often blurred, demanding meticulous, multidisciplinary investigation to accurately interpret these primordial clues. Distinguishing between natural fossil formations and potential artifacts of ancient civilizations presents a complex challenge for paleontologists and astrobiologists alike. The core difficulty lies in the inherent similarity between certain natural mineral structures and fabricated objects, which can obscure our ability to identify signs of past technological activity. Many mineral formations, such as concretions, mineralized biological tissues, or pseudofossils, can produce features that superficially resemble manufactured tools or structures. These natural formations often form through geological processes, pressure, mineral deposition, or biological activity that can mimic the geometric regularity or material composition of human-made objects. One significant obstacle is the prevalence of abiotic processes that produce structured patterns. For example, crystal growth can generate symmetrical shapes or layered patterns that resemble tool marks or carved surfaces. Similarly, mineralized microbial colonies or biofilm structures may produce intricate textures that could be mistaken for crafted surfaces. Differentiating between these naturally occurring features and potential artifacts thus demands meticulous analysis, often involving multiple techniques such as high-resolution imaging, spectroscopy, and isotopic studies. Another complication stems from the rarity of well-preserved contextual clues. Artifacts of a civilization, if they ever existed in deep time, would likely be subject to extensive geological alteration, erosion, and metamorphism, which can obscure or destroy their original characteristics. Over hundreds of millions of years, even the most resilient structures can be transformed into indistinguishable mineral deposits. Without clear contextual evidence, such as associated tools, distinct manufacturing marks, or stratigraphic positioning, it becomes exceedingly difficult to determine whether a fossilized feature is the product of natural processes or indicative of intelligent activity. Furthermore, our understanding of the full range of natural geological phenomena is still incomplete. Some structures might represent unexplained natural formations that challenge existing geological models, making the task of identification even more nuanced. As a consequence, scientists must approach potential anomalous fossils with a rigorous, multidisciplinary methodology, scrutinizing their morphology, composition, and context for clues that might differentiate natural origins from possible signs of ancient technology. This ongoing challenge naturally leads to the intriguing question: could certain fossilized structures indicate the presence of ancient machinery or tools? Fossilized structures that suggest the presence of ancient machinery or tools remain a contentious and fascinating aspect of paleoanthropological research. Unlike organic remains, such as bones or shells, these potential artifacts require careful analysis to distinguish genuine evidence from natural geological formations or mineral deposits. Nonetheless, certain peculiar features in the fossil record have prompted speculation about the existence of advanced technology in deep time, predating known human civilizations. One of the most debated examples involves anomalous, geometrically precise formations found in some sedimentary deposits. These structures often exhibit symmetry, regularity, and complex arrangements that are difficult to attribute solely to natural processes like mineral growth or erosion. For instance, some researchers point to intricately layered, metallic-looking inclusions within certain fossils, which could, in theory, represent remnants of rudimentary tools or mechanical devices. When viewed under microscopic analysis, these inclusions sometimes display patterns reminiscent of gear teeth, hinges, or other mechanical components. Such features, if verified, could imply the existence of ancient craftsmanship far beyond current archaeological understanding. However, critical examination emphasizes the importance of skepticism and rigorous validation. Many of these structures can be explained by mineral crystallization, pseudofossils, or other geological phenomena that mimic artificial constructs. For example, certain silicate formations can develop intricate geometries through natural mineral growth processes, leading to false positives in the search for ancient technology. Additionally, the preservation of metallic materials over millions of years is rare, and corrosion or mineral replacement often obliterates original metallic signatures, complicating identification. Furthermore, the context in which these structures are found plays a crucial role. Isolated anomalies may lack the contextual clues necessary to establish their artificial origin. Conversely, consistent patterns across multiple sites, correlated with other signs of advanced activity, would strengthen the case for ancient machinery. To date, while some findings remain intriguing, a definitive link between fossilized structures and ancient tools or machines has yet to be conclusively established. This ongoing investigation naturally leads to questions about the broader implications of fossil evidence. Specifically, whether the fossil record can support or contradict the hypothesis that pre-human civilizations once thrived on Earth, a topic that warrants careful exploration. The fossil record plays a pivotal role in evaluating the plausibility of pre-human civilizations, offering both supporting clues and notable contradictions. Traditionally, fossils serve as the primary window into Earth's deep past, revealing the evolution of life forms across billions of years. However, when it comes to identifying evidence of advanced, potentially industrialized civilizations predating humans, the record presents significant challenges. For one, the fossilization process itself is highly selective, favoring hard tissues like bones and shells, while soft materials, such as organic artifacts or technological remnants, rarely fossilize. This inherent bias complicates efforts to recognize signs of ancient technological activity or societal complexity that might have existed before human emergence. Furthermore, many purported signs of ancient civilizations, such as artificial structures or modified materials, are often dismissed or overlooked because they resemble natural formations or are too subtle for current detection methods. For instance, certain anomalous mineral deposits or unusual patterns in sediment layers could suggest past activity, but the absence of definitive, durable artifacts hampers conclusive interpretation. Conversely, some discoveries, like anomalous isotopic ratios or unusually preserved materials, have fueled hypotheses of prior technological civilizations, yet these findings often lack the contextual evidence necessary to definitively support such claims. On the other hand, the fossil record does provide some indirect support for the possibility of pre-human civilizations. For example, the sudden appearance of certain mineral deposits or the presence of unusual microfossil assemblages in specific strata could hint at large-scale environmental alterations caused by advanced activity. Still, these signals are often ambiguous, and distinguishing between natural geological processes and anthropogenic effects remains a significant obstacle. Overall, while the fossil record offers tantalizing glimpses into Earth's deep history, it largely contradicts the idea of well-preserved, unmistakable traces of ancient civilizations predating humans. The scarcity of direct evidence underscores the need for more sensitive and innovative detection methods, both to interpret ambiguous findings and to explore uncharted geological records, raising the question, what new fossil discovery techniques could enhance our search for evidence of ancient civilizations? Advancements in fossil discovery techniques hold immense promise for unveiling evidence of ancient civilizations that have long eluded detection. Traditional methods, such as surface surveys and excavation, often rely heavily on visible or accessible remains. However, recent innovations in technology are expanding our investigative capabilities into previously inaccessible or overlooked domains. One groundbreaking approach is the use of ground-penetrating radar, GPR, combined with 3D seismic imaging. These non-invasive techniques enable researchers to peer beneath layers of sediment or rock without disturbing the site, revealing buried structures or artifacts that might resemble architectural remains or artificial formations. When integrated with machine learning algorithms, these methods can analyze vast datasets to identify anomalous patterns suggestive of deliberate construction or unnatural alignments, thus narrowing potential excavation targets. Another promising development is spectral imaging, which captures data across multiple wavelengths, visible, infrared, and ultraviolet, to detect subtle, chemical or mineralogical signatures indicative of artificial alteration. For instance, certain pigments, metals, or synthetic compounds used in ancient construction might leave spectral fingerprints distinguishable from natural mineral deposits. This technique can be applied remotely via aerial drones or satellites, allowing for large-scale surveys of remote or inaccessible terrains. Additionally, innovations in isotope analysis, particularly with clumped isotope thermometry, allow scientists to determine formation temperatures and environmental conditions with high precision. When applied to fossils or mineral deposits, these methods can highlight anomalous thermal histories or chemical processes that deviate from natural geologic patterns, potentially pointing toward human or non-human technological activity. The emergence of micro-CT scanning also enhances our ability to investigate small or intricately preserved artifacts embedded within rock matrices. By providing high-resolution, three-dimensional visualizations, micro-CT can reveal intricate details of construction techniques or tool marks that may suggest intent or craftsmanship of an artificial origin. Together, these innovative techniques significantly broaden our capacity to detect subtle, buried, or altered features that might indicate the presence of ancient, non-human civilizations. As technology continues to evolve, so too does our potential to uncover the hidden chapters of Earth's distant past, blurring the line between natural formations and constructed artifacts. Archaeological anomalies that hint at ancient, non-human civilizations often defy conventional understanding and compel researchers to re-evaluate long-held assumptions about human history. These anomalies encompass a diverse array of artifacts and structures that, upon closer inspection, appear inconsistent with known technological capabilities, chronological frameworks, or cultural contexts. One of the most compelling categories involves unusually precise or sophisticated construction techniques that seem to surpass the technological limitations of their purported time periods. For example, certain megalithic structures exhibit extraordinary geometric precision and alignment with celestial bodies, suggesting an advanced knowledge of astronomy and engineering that predates the known development of such skills by human civilizations. These anomalies challenge the idea that ancient humans alone could have executed such feats without external aid or knowledge transfer from a more advanced source. Additionally, artifacts composed of materials that seem incompatible with their supposed age or origin present intriguing questions. For instance, the discovery of advanced metal alloys or synthetic materials in contexts dating far earlier than their known technological emergence hints at an alternative source of technological knowledge, possibly from a non-human civilization. Similarly, unusual isotopic compositions or unexplained residues on artifacts can suggest processes or origins beyond human capabilities. Unearthly or inexplicable artifacts, such as carved stones with symbols that bear no resemblance to known languages or scripts, or objects with unknown manufacturing marks, further deepen the mystery. These artifacts may exhibit craftsmanship or purpose that does not align with any recognized ancient culture, hinting at a different intelligence or civilization that once thrived in the distant past. Structures that defy geological explanations, such as perfectly straight roads crossing rugged terrain or massive subterranean chambers with no clear access points, also stand out as anomalies. Their construction methods and purpose often remain enigmatic, sparking theories that they might have been built by an intelligent, non-human species with knowledge and technology lost to time. Collectively, these anomalies serve as compelling puzzle pieces. They invite us to reconsider the narrative of human uniqueness and ponder whether our ancestors were part of a broader, more complex history, possibly involving civilizations that existed long before recorded history, and perhaps even beyond human origin. Next, we will explore how these unexplained artifacts and structures pose significant challenges to established archaeological paradigms, prompting a reassessment of our understanding of ancient history. Unexplained artifacts and structures continue to challenge the foundational assumptions of mainstream archaeology, prompting scholars to reconsider the timeline and complexity of human and pre-human activity. Traditional paradigms posit that human civilization emerged relatively recently, roughly 10,000 years ago, built upon a linear progression from primitive societies to advanced cultures. Yet, numerous anomalies defy this narrative, suggesting that certain artifacts or edifices are far older or technologically advanced than previously believed. These anomalies often possess qualities that are difficult to reconcile within accepted frameworks, thereby fostering ongoing debate and investigation. One key challenge lies in artifacts whose age cannot be reliably determined or whose craftsmanship exceeds known technological capabilities of their purported periods. For example, intricate stone carvings, Machine-like tools or metallic objects discovered in strata associated with ancient periods can seem inexplicable, raising questions about possible lost knowledge or earlier civilizations. Similarly, structures like megalithic monuments, such as certain stone circles or enigmatic foundations, exhibit architectural sophistication that is not easily explained by the technological means available at the supposed time of construction. These anomalies prompt archaeologists to question whether our understanding of technological evolution is complete or whether some artifacts might have origins predating the accepted timeline. Moreover, some artifacts exhibit signs of advanced manufacturing techniques, precise machining, advanced metallurgy, or materials with properties that seem inconsistent with the era's known capabilities. These anomalies could suggest the existence of knowledge transfer, lost civilizations, or even extraterrestrial involvement. But they also open the door to alternative hypotheses like the Silurian Hypothesis, the idea that an ancient, technologically advanced civilization may have existed long before recorded history. If such artifacts are genuine and their dating accurate, they could imply that human history is far more complex and layered than the current archaeological record indicates. The persistent presence of these anomalies has led researchers to question whether current excavation methods and dating techniques might overlook or dismiss evidence that doesn't fit prevailing paradigms. As a result, unexplained artifacts serve as compelling catalysts for re-evaluating assumptions about human progress and the potential existence of ancient civilizations that have left behind subtle but enduring traces. This ongoing puzzle invites a broader perspective, one that considers the possibility of long-lost cultures shaping history in ways we are just beginning to comprehend. Among the most compelling archaeological mysteries that might be reinterpreted through the lens of the Silurian hypothesis are the enigmatic structures whose origins and purposes remain stubbornly elusive. For centuries, monuments such as the megalithic stone circles of Europe, the massive stone heads of Easter Island, and the intricate, precisely aligned Egyptian pyramids have inspired awe and speculation. Traditionally, these sites have been attributed to ancient civilizations with advanced, yet human-specific, engineering knowledge. However, when considering the possibility of prior, perhaps technologically advanced, civilizations predating known history, these structures could take on new significance. One intriguing example is the construction of Göbekli Tepe in Turkey, often regarded as the world's oldest known megalithic site. Its monumental stone pillars, decorated with carved animals and abstract symbols, seem to appear suddenly in the archaeological record, with no clear antecedent. Could these be remnants of an earlier civilization that possessed advanced construction techniques or symbolic knowledge lost to subsequent cultures? Similarly, the vast Nazca lines in Peru, sprawling geoglyphs visible only from the air, challenge conventional understanding of prehistoric art and engineering. Some researchers suggest that their scale and precision might hint at knowledge of aerial viewing or remote surveying techniques, possibly inherited from earlier, more technologically adept societies. Further, the remarkable precision of the ancient Egyptian pyramids and the megalithic temples of Malta exhibit construction methods that seem to transcend the capabilities of their purported time periods. The alignment of these structures with celestial bodies, their sophisticated internal acoustics, and the sheer scale of the stonework invite questions about the technological prowess of their builders. Under the Silurian hypothesis, these features could be reinterpreted as the remnants of a long-lost civilization with access to now-forgotten engineering principles or even alien-assisted technology. In essence, these archaeological mysteries, once viewed through a conventional lens, may reveal new layers of meaning if we entertain the possibility of prior civilizations. Their inexplicable features could be the surviving vestiges of a more ancient, more technologically advanced society that left behind enigmatic monuments, waiting to be understood from a radically different historical perspective. Ancient megastructures and unconventional construction techniques serve as compelling clues when exploring the possibility of prior advanced civilizations. Unlike typical archaeological remains, these massive structures often defy easy explanation through known historical or technological capabilities. For instance, some sites feature colossal stones meticulously fitted together without mortar, with alignments and geometries that suggest advanced understanding of mathematics and astronomy. Structures such as the megalithic stone circles, massive terraces, or complex aqueduct systems often exhibit engineering prowess that surpasses what is considered achievable with the known tools and methods of ancient societies. What makes these structures particularly intriguing is their scale and precision, which imply the use of sophisticated planning, knowledge of materials, and possibly even machinery that predates traditional historical timelines. Unusual construction techniques, such as the precise carving and transportation of gigantic stones over great distances, may hint at lost technologies or methods that have since been forgotten. For example, some researchers point to the use of advanced geopolymer concretes or other composite materials that seem out of place in their apparent time period, suggesting that the builders possessed knowledge now lost to history. Furthermore, anomalies in construction styles, such as the use of multiple layers of different materials, intricate geometric alignments, or the presence of structures that seem to serve no immediate practical purpose, can indicate a symbolic or cosmological significance. These features may reflect a level of societal complexity and technological sophistication that challenges the conventional chronological narrative. Importantly, the discovery of such structures often prompts questions about historical continuity and the potential existence of earlier, more advanced societies. Their construction methods, scale, and purpose can point toward a collective knowledge base that predates known civilizations, possibly tied to a global or widespread culture that once thrived and then vanished, leaving behind enigmatic remnants. This leads naturally to the question of where these structures are found and how they might be preserved, particularly in environments less accessible or visible today. This consideration introduces the role of underground or submerged archaeological sites, which could harbor the remnants of these mysterious constructions, potentially offering vital clues to the existence of prior civilizations. Underground and submerged archaeological sites serve as critical focal points within the Silurian hypothesis, as they may harbor evidence of advanced civilizations predating known human history. These sites, often concealed beneath layers of sediment, water, or debris, present unique challenges and opportunities for researchers seeking to uncover alternative narratives of human or pre-human development. Their significance lies in the potential to preserve structures, artifacts, or environmental conditions that have remained largely untouched by natural erosion or modern development, thus offering invaluable clues about past civilizations that might have thrived long before recorded history. Subterranean sites, such as buried cities or networked tunnels, could contain remnants of sophisticated infrastructure, such as elaborate foundations, tools, or even organic materials, locked away beneath centuries of Earth accumulation. These sites might also be protected from surface-level disturbances, making them ideal repositories for preserved evidence of technological or cultural complexity. Similarly, submerged archaeological locations, sunken cities, shipwrecks, or submerged landscapes pose tantalizing possibilities for discovering evidence of a civilization lost to rising sea levels or catastrophic events. For example, submerged coastal settlements might reveal artifacts and architectural features that challenge conventional timelines, suggesting an earlier period of human or intelligent activity. The challenge, however, lies in locating these elusive sites amidst the vastness of the Earth's surface and underwater environments. Natural processes such as sedimentation, tectonic shifts, and water currents often obscure or destroy surface indicators, making traditional excavation impractical or incomplete. Consequently, the identification and study of these hidden sites require innovative approaches that blend traditional archaeology with cutting-edge technology. Herein lies the importance of interdisciplinary collaboration, combining geological surveys, environmental studies, and advanced sensing techniques to piece together the puzzle of ancient concealed civilizations. Understanding the role of underground and submerged sites within the Silurian hypothesis underscores the necessity of leveraging modern technological advancements. As we explore how tools like ground-penetrating radar and LiDAR can revolutionize archaeological discovery, it becomes clear that these innovations hold the key to unlocking secrets buried deep beneath our feet or beneath the waves, potentially rewriting the story of human history itself. Modern technological advancements such as ground-penetrating radar, GPR, and light detection and ranging, LiDAR, have revolutionized the way archaeologists and researchers uncover and analyze hidden sites. These tools provide non-invasive means to explore beneath the Earth's surface, revealing structures and landscapes that remain concealed from surface observation. Their ability to detect subsurface anomalies without excavation minimizes disturbance to potential archaeological deposits, preserving integrity while expanding investigative reach. Ground-penetrating radar operates by emitting high-frequency radio waves into the ground. When these waves encounter buried objects, voids, or stratigraphic changes, they reflect back signals that can be captured and interpreted to produce detailed images of what's beneath the surface. GPR is particularly effective in deciphering complex stratigraphy or identifying buried walls, foundations, or artifacts in challenging terrains. Its real-time imaging capability allows researchers to target specific areas for excavation or further analysis, making the process more efficient and precise. LiDAR, on the other hand, utilizes laser pulses from aircraft or drones to generate highly detailed topographic maps. This technology is especially advantageous in dense forested environments where traditional survey methods are hindered by vegetation cover. LiDAR can penetrate canopy layers to reveal underlying archaeological features such as ancient city layouts, road networks, or earthworks that have been obscured over centuries. Its high-resolution data enables the creation of digital elevation models that can be analyzed for subtle terrain modifications indicative of past human activity. Both GPR and LiDAR facilitate large-scale surveys that would be impractical or impossible through manual excavation alone. They help identify promising sites, guide targeted excavations, and reconstruct historical landscapes with unprecedented accuracy. These technologies also enable researchers to compare findings across different regions, detecting patterns or anomalies that might suggest the presence of long-forgotten civilizations. However, while these tools significantly enhance discovery capabilities, they also introduce new complexities. Interpreting the vast amount of data they produce requires specialized expertise, and distinguishing genuine archaeological features from natural formations remains a challenge. As we leverage these technological marvels, it becomes essential to address the subsequent question: what are the challenges of verifying the authenticity and dating of anomalous artifacts? Verifying the authenticity and accurate dating of anomalous artifacts presents a formidable challenge, primarily due to the limitations of current technological methods and the inherent complexities of the artifacts themselves. One of the foremost difficulties lies in distinguishing genuine ancient artifacts from modern imitations or natural formations that resemble manufactured objects. The scientific techniques employed, such as radiocarbon dating, thermoluminescence, or stratigraphic analysis, are powerful but not infallible. These methods rely on assumptions about the preservation of certain isotopic signatures or the context in which artifacts are found, which can sometimes be compromised by environmental factors, contamination, or post-depositional processes. Furthermore, anomalous artifacts often exist at the fringes of established archaeological understanding, which can lead to skepticism and rigorous scrutiny. For example, an artifact with unusual material composition or an enigmatic construction technique might initially be dismissed as a natural formation or a modern fabrication. However, without corroborating evidence from multiple sources, such as consistent stratigraphic placement, corroborative dating methods, or contextual artifacts, such conclusions remain tentative. The challenge intensifies when artifacts are fragmentary, eroded, or altered by natural processes over millennia, obscuring their origin and purpose. Another complicating factor is the potential for natural geological formations to mimic artifacts. Certain mineral deposits, crystal growths, or rock arrangements can resemble crafted objects in shape or texture, leading to misinterpretations. Distinguishing between deliberate human modification and natural processes requires a detailed understanding of geology, mineralogy, and formation dynamics. Experts often employ microscopic analysis, chemical composition tests, and 3D imaging to discern subtle signs of tool marks or manufacturing techniques that natural formations lack. The difficulty in verification underscores the importance of multidisciplinary approaches, combining archaeology, geology, chemistry, and even advanced imaging technologies to build a comprehensive picture of an artifact's origins. As research progresses, developing more refined criteria for authenticity and improved contextual analysis becomes essential in preventing misinterpretations and advancing our understanding of potential ancient civilizations. While the possibility that some artifacts might be misinterpreted natural formations remains a compelling consideration, rigorous scientific scrutiny helps differentiate genuine artifacts from geological phenomena. Natural formations such as mineral deposits, weathered rock structures, or crystalline formations can occasionally resemble man-made objects, especially when eroded or altered over millennia. However, discerning authentic artifacts from natural features hinges on understanding their formation processes, contextual clues, and the presence of consistent, purposeful design elements. One key approach involves analyzing the morphology and material composition of suspect objects. Genuine artifacts typically exhibit characteristics of manufacturing, such as tool marks, consistent geometry, or evidence of deliberate shaping, features unlikely to result from purely natural processes. For instance, symmetrical or patterned surfaces, uniform edges, or elements that suggest assembly can point toward artificial origins. Conversely, natural formations often display irregular, fractal, or fractal-like patterns resulting from mineral crystallization, erosion, or geological activity. Additionally, contextual examination plays a crucial role. Artifacts found in stratified layers with other signs of ancient habitation, such as tools, pottery, or organic remains, are more likely to be genuine. Conversely, isolated objects lacking contextual association might warrant further scrutiny to rule out natural origins. Geographic and geological assessments further aid this differentiation. Understanding local mineralogy and geomorphology helps identify whether a formation results from natural processes like volcanic activity, sedimentation, or mineral precipitation. Advanced analytical techniques also bolster identification efforts. Spectroscopic analysis can reveal material compositions consistent with human manufacturing versus natural mineral growths. Imaging technologies, including 3D scanning and electron microscopy, can uncover subtle manufacturing traces invisible to the naked eye. These methods, combined with interdisciplinary expertise from geology, archaeology, and materials science, form a comprehensive framework to evaluate potential artifacts. Recognizing these distinctions is vital, especially when considering the tantalizing possibility of ancient, non-human civilizations. Clarifying what is natural versus man-made not only prevents false positives, but also sharpens our focus on genuine anomalies, those rare clues that might truly suggest a long-lost chapter of planetary history. As we move forward, understanding how to differentiate natural formations from artifacts prepares us for the next step, identifying the unmistakable signatures of ancient machinery or infrastructure. Detecting the remnants of an ancient civilization's machinery or infrastructure requires a keen eye for subtle yet telling technological signatures embedded within the Earth's fabric. Unlike surface artifacts, which may erode or become buried over millennia, the telltale signs of past engineering efforts often manifest as anomalies within electromagnetic, gravitational, or seismic data. These signatures, if identified and correctly interpreted, could serve as indirect evidence of long-lost technological activity. Electromagnetic anomalies are among the most promising indicators. Civilizations that engaged in large-scale industrial or technological activities would have generated distinctive electromagnetic fields. For example, remnants of underground power grids, machinery, or communication networks might induce localized magnetic disturbances or anomalous electrical conductivity in subsurface materials. These disruptions could be detected through geophysical surveys utilizing magnetometers and electromagnetic induction methods. Such anomalies tend to be persistent and spatially coherent, contrasting with natural variations caused by mineral deposits or geological processes. Gravitational signatures offer another avenue for discovery. Large-scale artificial structures, such as extensive underground facilities or massive machinery, would exert subtle yet measurable gravitational effects. High-precision gravimetric surveys can detect density anomalies that do not correspond to known natural formations. For instance, a buried complex of machinery or infrastructure might produce a localized increase in density, distinguishable from surrounding geological features. Over time, changes in gravitational readings could also reflect ongoing processes, hinting at active or recently active artificial systems. Seismic data provides yet another window into hidden ancient structures. Engineered formations, especially those built with materials or construction techniques different from natural geology, can produce characteristic seismic reflections or anomalies. When seismic waves encounter interfaces between natural rock and artificial structures, such as tunnels, chambers, or foundations, they produce reflections with distinctive signatures. Advanced seismic imaging can reveal these features at depths and scales that are otherwise inaccessible, offering compelling clues about historical engineering. In sum, a comprehensive analysis that combines electromagnetic, gravitational, and seismic data enhances our ability to detect the faint signatures of ancient technological civilizations. By meticulously studying these anomalies, researchers can uncover indirect, yet persuasive evidence, pointing toward a technologically advanced past, even if no surface artifacts remain. Such discoveries could radically reshape our understanding of human history and our place in a broader cosmic narrative. Anomalies detected within electromagnetic, gravitational, or seismic data can serve as compelling indicators of potential artificial origins, particularly when they deviate from natural geophysical patterns. Electromagnetic anomalies, for instance, may manifest as unusual magnetic fields or persistent electrical signals that cannot be readily explained by known natural processes. Such signals might resemble those produced by large-scale electrical infrastructure or sophisticated technological systems, especially if they exhibit regularity, coherence, or frequencies that are unlikely to result from natural phenomena. For example, localized magnetic anomalies could suggest the presence of buried or concealed energy sources or ancient electromagnetic devices that once powered or controlled complex systems. Gravitational anomalies, on the other hand, often point to irregular mass distributions beneath the Earth's crust. When these anomalies are localized and persistent, they could indicate the presence of artificially constructed structures or accumulations of unusual materials that are inconsistent with natural geology. In some cases, these gravitational irregularities might hint at the existence of large, engineered constructs, such as underground chambers, energy containment facilities, or even previously active energy sources that have altered the local gravitational field in detectable ways. Seismic data offers another window into potential artificial structures or systems. Anomalous seismic activity, such as unexplained vibrations, resonance effects, or patterns that do not conform to typical tectonic movements, may suggest the presence of engineered energy systems or machinery. For example, rhythmic, seismic signals might resemble the vibrations produced by pulsating energy sources or mechanical devices that operated within ancient constructs. Additionally, unusual seismic reflections or echoes could indicate hidden tunnels, chambers, or layered structures that were intentionally designed to contain or harness energy. When these anomalies are observed in conjunction, they can form a pattern that strongly hints at the existence of past or even current artificial systems. Such evidence invites further investigation into their origins, seeking clues that could reveal the nature of ancient energy sources or power systems. This leads naturally into the next inquiry. What specific signs might indicate the presence of these enigmatic energy sources, those mysterious remnants of technology that could have powered civilizations long gone? Ancient energy sources or power systems, if they existed, might leave behind subtle yet discernible traces embedded within geological or archaeological records. Unlike the modern energy infrastructure, which relies on standardized materials and recognizable technological signatures, these primordial systems could have employed naturally available resources or early forms of energy harnessing that are less obvious to the casual observer. For instance, evidence of large-scale geothermal manipulation or artificial thermal anomalies could suggest the existence of ancient energy extraction techniques. Such features might appear as unusual heat flow patterns or mineral deposits formed under anomalous conditions that defy natural explanations. Additionally, altered mineral compositions or unusual isotopic ratios within certain rocks could indicate past technological activity involving energy conversion or storage. For example, concentrations of rare isotopes or anomalous electromagnetic properties might point toward the use of early electromagnetic or radiative technologies. In some cases, evidence of artificial structures, such as large, precisely aligned stone arrangements, may have served as part of energy collection or transmission systems, especially if their orientation correlates with celestial or magnetic phenomena. Furthermore, the discovery of artifacts, composed of unconventional alloys or synthetic materials impossible to replicate with ancient known techniques, could hint at advanced metallurgical processes. Such materials might have been used to construct components of power systems, like batteries or energy regulators, that predate known civilizations. The existence of these artifacts, if proven authentic, could revolutionize our understanding of ancient technological capabilities. In some scenarios, remnants of electromagnetic or acoustic energy systems could have left faint but detectable imprints in the Earth's crust or magnetic field. For example, localized magnetic anomalies or persistent electromagnetic disturbances might be associated with ancient energy infrastructure. Over millennia, these signals could have decayed or been masked by natural processes. But with sensitive modern technology, their subtle signatures might still be recoverable. All these potential indicators offer tantalizing clues that ancient civilizations might have harnessed energy sources on scales and complexities previously thought impossible. Recognizing such signs could provide profound insights into our planet's hidden technological past and open new avenues for detecting ancient innovations long buried beneath time. Remnants of ancient communication systems or data storage, if they existed, could potentially be detectable today through various subtle geological and chemical signatures. While traditional archaeological artifacts like ceramics or metal relics are the most obvious indicators of past technological activity, advanced data storage methods, particularly those involving novel materials, may leave more elusive traces that require specialized detection techniques. For instance, if an ancient civilization employed nanotechnology-based storage media or utilized advanced materials to encode information, these could manifest as distinctive mineralogical or chemical anomalies embedded within the Earth's strata. One avenue for detection involves analyzing isotopic or mineralogical anomalies associated with the fabrication of such materials. Certain nanomaterials, like engineered nanoparticles or layered composites, may incorporate elements or isotopic ratios that deviate from natural abundances. Over time, these materials could alter local geochemistry, creating identifiable signatures detectable through high-resolution spectrometry or mass spectrometry. Similarly, the presence of synthetic polymers or carbon-based nanostructures, such as graphene-like sheets, might produce characteristic patterns in the organic or inorganic fraction of sediments, especially if they have persisted for millennia. Moreover, advanced materials often exhibit unique physical properties that could influence the surrounding geological environment. For example, Some nanostructures might catalyze mineral transformations or serve as nucleation sites for mineral deposits, resulting in microstructures distinguishable under electron microscopy. These microstructural features could serve as indirect evidence of ancient technological activity. Additionally, if a civilization employed electromagnetic or acoustic communication methods using materials capable of sustaining such signals, subtle imprints might remain in the form of preserved electromagnetic or vibrational anomalies within mineral matrices. While the detection of such traces presents significant challenges, given the potential for degradation, contamination, and the subtlety of signals, ongoing advances in analytical technologies bolster the possibility. Techniques like synchrotron radiation analysis, nanoscale imaging, and isotopic fingerprinting are continually improving, opening new frontiers for uncovering evidence of ancient communication or data storage systems embedded deep within the geological record. As our understanding deepens, the prospect of identifying traces of advanced, possibly nanotechnological civilizations becomes an increasingly tangible scientific pursuit. Nanotechnology and advanced materials, by their very nature, possess unique physical and chemical signatures that can potentially be preserved within the geological record over extended periods. Unlike traditional materials, these innovations often involve elements or molecular structures that are either rare on Earth or require specific conditions to form. When such materials are produced or utilized on a large scale, whether through manufacturing, waste disposal, or accidental deposition, they can leave behind subtle but detectable traces embedded in sediments, mineral formations, or even ice cores. One key aspect is that nanomaterials often have distinctive isotopic ratios or crystal structures that differ markedly from naturally occurring counterparts. For example, engineered nanoparticles synthesized with specific isotopic compositions or unique surface coatings may resist natural degradation, thus persisting within strata for millennia. Over time, these particles can become incorporated into sediment layers, mineral deposits, or fossilized materials, effectively serving as a geological fingerprint of technological activity. Similarly, advanced materials like high-performance composites or novel alloys may undergo mineralization processes, creating distinctive mineral assemblages that can be distinguished through geochemical analyses. Furthermore, the detection of such traces hinges on our ability to identify anomalies in the Earth's geological history, unusual concentrations of specific elements, isotopic deviations, or mineral morphologies that cannot be explained by natural processes alone. These signatures may be subtle, requiring high-resolution analytical techniques such as mass spectrometry, electron microscopy, or synchrotron-based imaging. The challenge lies in differentiating between anthropogenic signatures from recent industrial activity and those potentially originating from ancient technological civilizations, necessitating a deep understanding of natural background variability. As research progresses, it becomes increasingly feasible to search for these traces in well-preserved geological archives. The goal is to identify persistent, anomalous markers that could suggest the presence of advanced materials produced by a civilization that predates our own. This pursuit naturally leads to the question of how modern remote sensing technologies, particularly satellite imaging, might assist in uncovering surface-level or subsurface anomalies indicative of past technological activity, setting the stage for a broader exploration of detection methods. Satellite imaging and remote sensing have revolutionized the way we search for signs of ancient or extraterrestrial technological activity, offering an unprecedented vantage point that terrestrial archaeology alone cannot provide. These technologies enable scientists to scan vast, inaccessible regions such as dense forests, deep ocean floors, and remote desert landscapes where anomalies might otherwise remain hidden. High-resolution multispectral and hyperspectral imaging capture data across various wavelengths, revealing subtle differences in mineral composition and surface features that could indicate artificial structures or modifications. Thermal imaging, in particular, can detect heat signatures associated with recent or residual energy sources, providing clues for potential technology remnants even after millennia. Remote sensing tools also facilitate the identification of anomalous geometries that deviate from natural geological formations, such as regular patterns, straight lines, or rectilinear shapes that are often considered indicative of artificial origin. By analyzing these features in their spatial context, researchers can prioritize sites for targeted ground investigations, thereby optimizing resource allocation and minimizing false leads. Furthermore, spectral analysis allows for the detection of materials that are uncommon in natural mineral deposits but are associated with technological processes, such as specific alloys or synthetic compounds. However, while satellite-based technologies are invaluable for initial screening, their effectiveness hinges on the ability to interpret data accurately. Variations in natural geology, erosion, and environmental factors can produce surface features that mimic artificial signatures, complicating the identification process. The resolution of imaging systems, though continually improving, may still be insufficient to resolve fine details necessary for definitive conclusions. Additionally, the sheer volume of data generated necessitates sophisticated algorithms and machine learning models capable of distinguishing genuine anomalies from benign natural features. As we deepen our reliance on these remote sensing techniques, an inherent challenge emerges, discerning between naturally occurring mineral formations and potential technological signatures. This ongoing difficulty underscores the importance of integrating multi-sensor data, ground truthing efforts, and interdisciplinary expertise to avoid misinterpretation. Understanding these nuances is crucial for advancing our search for evidence of ancient or advanced civilizations, especially when natural geological processes can produce features that closely resemble artificial constructs. One of the most significant hurdles in identifying potential artificial technological signatures lies in differentiating them from complex natural mineral formations. Many geological processes produce structures that can mimic the appearance of fabricated artifacts, making the task akin to distinguishing a carefully crafted sculpture from a naturally eroded rock formation. For instance, mineral deposits such as banded iron formations, stromatolites, or certain mineral veins can develop shapes and layered patterns that superficially resemble tools or machinery remnants. These formations, formed over millions of years through mineral precipitation, sedimentation, or biological activity, can exhibit regularity, symmetry, or unusual compositions that might be mistaken for artificial origins. A core challenge is that natural mineral formations are often highly variable and influenced by environmental factors, leading to a wide spectrum of shapes and textures. This variability complicates the development of clear criteria to reliably distinguish between natural and artificial structures. Furthermore, many mineral signatures, such as specific isotopic ratios or mineral compositions, can overlap with those expected from technologically altered materials, especially if ancient civilizations employed minerals with unique properties or processing techniques. The issue is compounded by the fact that natural processes can sometimes produce anomalous features, such as crystalline structures or mineral concretion, which could be misinterpreted as evidence of past technological activity. Another significant obstacle is the resolution and scope of current detection technologies. Remote sensing methods like satellite imagery, ground-penetrating radar, or spectroscopic analysis may lack the sensitivity or specificity needed to discern subtle artificial modifications embedded within complex geological backgrounds. Distinguishing a faint, artificially induced pattern from a naturally occurring one requires an understanding of the context and formation history of the site, information that is often incomplete or obscured. Overall, the challenge hinges on the inherent ambiguity of geological features, the overlapping signatures of natural and artificial origins, and the limitations of current detection tools. Addressing these issues demands not only refined analytical techniques, but also a comprehensive understanding of geological processes to develop reliable criteria for identifying genuine technological signatures amidst the natural mineral landscape. Looking ahead, advances in technology could radically enhance our capacity to make these distinctions more confidently. Advancements in technology hold significant promise for enhancing our capacity to detect ancient technological signatures, pushing the boundaries of what we can uncover about potential pre-human civilizations. One of the most promising avenues involves the development of more sensitive and comprehensive remote sensing tools. Improvements in satellite imaging, for instance, can enable us to identify subtle anomalies in Earth's surface that may indicate past technological activity, such as unexplained geophysical alterations or artificial structures concealed beneath layers of sediment. High-resolution spectroscopy, coupled with machine learning algorithms, can analyze vast datasets to pinpoint anomalous mineral compositions or unusual energy signatures that are unlikely to result from natural processes alone. Furthermore, advancements in geophysical survey methods, such as ground-penetrating radar, seismic tomography, and magnetic resonance imaging, allow for more detailed subsurface exploration without invasive digging. These tools can reveal buried artifacts or infrastructure that may have been deliberately hidden or simply decayed over time. As these methods become more precise and affordable, their application could expand from targeted searches to systematic, global scans for signs of ancient engineering. Another critical area is the refinement of dating techniques and isotopic analysis. Enhanced mass spectrometry and radiometric methods can improve our ability to date organic and inorganic materials with unprecedented accuracy, helping to establish timelines for potential technological activity. When combined with geochemical signatures, these techniques could identify periods of anomalous energy use or material processing that align with technological activity, even if physical structures no longer exist. Emerging fields like artificial intelligence and big data analytics also offer transformative potential. By training algorithms on known natural and artificial signatures, scientists can develop predictive models that flag potential artifacts or signatures of ancient technology. These models could process data across multiple disciplines: geology, chemistry, physics, integrating diverse signals into cohesive assessments. As technological capabilities advance, so too does our capacity to peer deeper into Earth's history and perhaps uncover evidence of civilizations long past. These innovations will not only increase our chances of detecting faint signatures, but also refine our understanding of what constitutes technological activity in the geological record. Such progress will be crucial in addressing the profound question of whether human civilization is truly unique or merely the latest chapter in a much longer story of intelligent life on Earth. Several compelling theoretical models have been proposed to explore the possibility of civilizations existing prior to humanity, challenging the long-held assumption that human civilization is unique and recent in planetary history. These models often draw on interdisciplinary insights, combining geology, archaeology, astrophysics, and evolutionary biology to construct plausible scenarios for ancient, perhaps even extraterrestrial, intelligent life. One prominent framework is based on the concept of the Silurian Hypothesis itself, which posits that a technological civilization could have arisen millions of years ago and subsequently left minimal or ambiguous traces in the geological record. This model considers the longevity of planetary geological processes and the ways in which advanced societies might leave subtle signatures, such as anomalous isotopic ratios, unusual mineral deposits, or fossilized technological artifacts, difficult to distinguish from natural phenomena. It emphasizes the importance of re-examining Earth's stratigraphy for overlooked or obscured evidence. Another influential model involves the idea of multiple, successive civilizations rising and falling across deep time, each potentially experiencing technological booms and collapses. This cyclical view suggests that civilizations might have existed during different geological epochs, with their remnants either eroded or buried beneath layers of sediment. These models often incorporate the concept of planetary resilience, where planetary processes like plate tectonics and climate shifts could erase or disperse signs of previous civilizations, complicating detection efforts. Furthermore, some models extend beyond Earth, contemplating the existence of intelligent extraterrestrial civilizations that may have existed on other planets or moons long before humans emerged on Earth. These scenarios often rely on astrophysical data, indicating that habitable environments could have existed elsewhere in the galaxy for billions of years, providing ample opportunity for life and potentially technological societies to develop independently and even reach advanced stages. Collectively, these models push the boundaries of our understanding of civilization timelines, prompting us to consider how planetary, biological, and technological factors intertwine over cosmic and geological scales. They challenge researchers to refine detection methods and broaden the scope of searching for signs of ancient, perhaps even pre-human, intelligence. This naturally leads to the question: how do these models incorporate planetary, biological, and technological factors? These models integrate planetary, biological, and technological factors by employing multidisciplinary frameworks that simulate the complex interplay between environment, life, and advanced civilizations. At their core, planetary parameters such as climate stability, geological activity, and atmospheric composition serve as foundational variables, influencing the potential for life to emerge and persist over geological timescales. For instance, models often incorporate data on planetary mass, orbital dynamics, and magnetic field strength, which collectively determine surface conditions and the planet's capacity to sustain habitable environments. Such factors are crucial in assessing whether a planet can support long-term biological evolution and, subsequently, the emergence of technological civilizations. Biological considerations are woven into these models through the inclusion of biological productivity, diversity, and resilience. They explore how life might adapt to varying environmental pressures and whether certain biosignatures could persist or be detectable after extensive geological or technological upheavals. These biological factors also influence planetary conditions via biogeochemical cycles, which can alter atmospheric composition and climate, thereby creating feedback loops that either promote or hinder the development of complex life. Incorporating this biological dimension allows models to evaluate the likelihood of multiple, distinct episodes of life emergence and potential civilization development, even on planets with tumultuous histories. Technological factors are integrated by examining the potential lifespan and detectability of civilizations based on their energy consumption, environmental impact, and technological signatures. These models consider how civilizations might progress or decline, factoring in the durability of their infrastructure and the likelihood of their activities, leaving detectable traces in planetary atmospheres or surfaces. They also simulate scenarios involving self-destruction, environmental collapse, or technological stagnation, which could truncate civilization development prematurely. By synthesizing these planetary, biological, and technological elements, the models provide a nuanced understanding of how various factors influence the trajectory of life and intelligence on other worlds. They reveal not only the conditions under which civilizations might arise, but also how planetary environments and biological resilience shape their evolution, persistence, or eventual disappearance. This comprehensive approach underscores the importance of interconnected systems in determining a planet's habitability over cosmic timescales, setting the stage for deeper insights into the potential diversity and longevity of extraterrestrial civilizations. The implications of these models for understanding planetary habitability and evolution are profound, reshaping our perspective on the potential diversity and resilience of life across the cosmos. By considering scenarios where advanced civilizations may have risen, persisted, or even vanished long before humans emerged, we recognize that habitability is not a static trait, but a dynamic process influenced by a multitude of factors. These models suggest that planets may have experienced multiple epochs of life, each driven by different environmental conditions, biotic innovations, or catastrophic events. Consequently, habitability becomes a temporal tapestry, with windows of opportunity that can open and close over geological timescales. One key implication is that planetary environments might possess a greater capacity for sustaining life than previously assumed. especially if life can adapt to or recover from extreme events. For instance, the existence of ancient, possibly now extinct civilizations implies that planets can support complex life forms for extended periods, even if current conditions seem inhospitable. This broadens the scope of where and when we might find signs of past life, encouraging us to refine our detection methods, to look for biosignatures or technological artifacts in ancient geological layers. Furthermore, these models challenge the traditional view of linear planetary evolution, highlighting the importance of stochastic events such as asteroid impacts, climate shifts, or supervolcanoes. In shaping the trajectory of life's development, they underscore the possibility that civilizations might rise rapidly in favorable conditions, only to fall due to unforeseen disasters, leaving behind subtle traces or complete silence. Such insights imply that planetary habitability is not merely a matter of initial conditions, but also of resilience and adaptability over cosmic timescales. In essence, these models deepen our understanding of the complex interplay between environmental factors and biological evolution. They suggest that the universe might be teeming with life of various forms and stages, some long gone, others thriving, prompting us to reconsider the rarity or uniqueness of Earth's evolutionary path. This richer framework for habitability encourages more nuanced searches for extraterrestrial life, rooted in the recognition that civilizations' lifespans and evolutionary trajectories are inherently unpredictable and deeply intertwined with their planetary histories. The models exploring ancient civilizations beyond human origins also offer intriguing insights into the Fermi paradox, the question of why, given the vastness of the universe and the high probability of extraterrestrial life, we have yet to detect definitive signs of other civilizations. These frameworks often posit that advanced societies may be inherently rare, transient, or prone to self-destruction, thereby contributing to the persistent silence we observe. One key aspect addressed by these models is the concept of technological longevity. Civilizations, whether terrestrial or extraterrestrial, might tend to collapse or regress due to internal factors such as environmental degradation, social upheaval, or technological fatigue. If civilizations are prone to self-inflicted annihilation or gradual decline before they can establish detectable long-term signals, this could explain the scarcity of observable extraterrestrial signals. Such a perspective reframes the Fermi paradox, not necessarily as a reflection of the universe's emptiness, but rather as a consequence of civilization's ephemeral existence. Furthermore, these models often invoke the idea of great filters, obstacles that prevent civilizations from progressing to detectable levels of interstellar communication or colonization. Catastrophic events, whether natural or anthropogenic, are central to this concept. For example, supervolcanic eruptions, asteroid impacts, or climate-altering pandemics could periodically reset civilizations, thereby reducing their chances of becoming detectable over cosmic timescales. This cyclical pattern of rise and fall implies that civilizations may exist only briefly within the window during which they are capable of communication, making their detection exceedingly unlikely. Additionally, some theories suggest that civilizations might intentionally or unintentionally choose to remain silent, either to avoid attracting potential threats or due to a philosophical stance of non-interference, further compounding the apparent silence. The combination of natural catastrophic resets and intentional non-disclosure could significantly diminish the probability of contact with extraterrestrial beings. In essence, these models weave a complex narrative, where the transience of civilizations, shaped by catastrophic events, serves as a primary explanation for the lack of contact. This naturally leads to questions about the factors influencing the rise and fall of societies, prompting an exploration of the critical role that such disruptive episodes play in the broader history of civilizations, both terrestrial and potentially extraterrestrial. Catastrophic events are central to many theoretical models that explore the rise and fall of ancient civilizations, often serving as pivotal turning points that dramatically reshape societal trajectories. In these models, natural disasters, such as massive volcanic eruptions, asteroid impacts, or abrupt climate shifts can act as both destructive forces and catalysts for transformation. When a civilization faces such a catastrophe, the immediate consequences often include widespread destruction, loss of life, and the collapse of complex infrastructure. These events can wipe out critical technological knowledge and social structures, plunging societies into chaos and regression. However, beyond their destructive capacity, catastrophic events can also serve as reset mechanisms, providing the conditions necessary for new civilizations to emerge. For example, a significant volcanic eruption might devastate an existing society, but leave behind fertile volcanic soils that promote agricultural rebirth. Similarly, climate shifts following a catastrophe can alter resource distribution, forcing populations to adapt or migrate, sometimes leading to cultural innovations or the development of entirely new societal frameworks. In this way, these events act as both destructive and creative forces, shaping the long-term evolution of civilizations. The timing and frequency of such catastrophic episodes are crucial factors in understanding patterns of rise and decline. Frequent, severe disasters may inhibit long-term societal stability, leading to cycles of growth and collapse. Conversely, infrequent but highly impactful events might explain abrupt societal disappearances, especially when combined with other stressors like resource depletion or social unrest. Additionally, these models highlight that the remnants of past civilizations are often fragmented or obscured by subsequent environmental and geological processes. Over millennia, sedimentation, erosion, and tectonic activity can bury or erode evidence of ancient societies, complicating archaeological efforts to reconstruct their histories. The interplay between catastrophe and preservation thus becomes a key consideration in understanding why some civilizations leave scant traces behind. This focus on the destructive power of natural events raises an intriguing question. Could these models also shed light on the puzzling absence of definitive evidence for pre-human civilizations? To explore this, it is essential to examine how catastrophic processes might erase or obscure signs of ancient societies predating human history. One of the central puzzles these models attempt to address is the conspicuous absence of definitive evidence for advanced pre-human civilizations, despite the plausibility of their past existence. Several hypotheses suggest that such civilizations could have existed but left behind minimal or highly ambiguous traces, complicating detection efforts. For example, some models propose that early civilizations might have constructed durable infrastructures, such as underground or submerged megastructures, that are difficult for current detection methods to identify. Alternatively, these civilizations could have employed resilient materials or engaged in rapid cyclical destruction and renewal processes, effectively erasing their archaeological footprints over geological timescales. Another explanation involves the notion of natural or anthropogenic catastrophic events that periodically reset the planet's surface record. Massive volcanic eruptions, asteroid impacts, or climate shifts that obscure or obliterate previous technological signatures. These catastrophic episodes could have created a reset button effect, making the survival of unambiguous artifacts or fossilized remains improbable. Consequently, the models posit that pre-human civilizations might have been transient, punctuated by environmental upheavals that prevented their legacy from enduring or becoming accessible to modern detection. Furthermore, some models incorporate the idea that early civilizations could have employed bioengineering or environmental modification techniques that leave subtle, difficult to distinguish marks in the geological record. For instance, large-scale alterations to sediment composition or subtle chemical signatures could be misinterpreted or overlooked within the vastness and complexity of the Earth's strata. These nuanced modifications might not stand out against natural background processes, thus contributing to the apparent silence across epochs. Despite these intriguing propositions, the validation of such models faces significant hurdles. The primary challenge lies in the inherent limitations of current detection technologies and interpretative frameworks. The geological record is inherently incomplete, subject to erosion, tectonic activity, and chemical alteration, making the search for ancient, faint signatures akin to finding a needle in a haystack. Moreover, the absence of direct, unequivocal artifacts raises questions about the reliability of indirect evidence and the risk of anthropogenic or natural misinterpretation. As we delve into the scientific and philosophical challenges of validating these models, it becomes clear that reconciling speculative hypotheses with empirical rigor requires both technological innovation and conceptual openness, a delicate balance between imaginative exploration and scientific skepticism. Validating models that posit the existence of pre-human or even non-human civilizations presents a host of formidable scientific and philosophical challenges. Foremost among these is the scarcity or complete absence of direct physical evidence. Unlike conventional archaeological artifacts, which can be subjected to radiometric dating, material analysis, and contextual interpretation, the hypothesized remnants of ancient, technologically advanced civilizations are often elusive or indistinguishable from natural geological formations. For instance, structures that could be interpreted as artifacts might be dismissed as naturally occurring formations, making definitive identification exceedingly difficult. From a scientific standpoint, the interdisciplinary nature of such investigations complicates validation efforts. Geologists, climatologists, archaeologists, and astrophysicists must collaborate to distinguish between natural and anomalous phenomena, often relying on indirect indicators like unusual isotopic signatures, cryptic microstructures, or anomalous sediment layers. However, the interpretive frameworks for these signals are still under development, and the risk of confirmation bias looms large. Additionally, the vast temporal scales involved, spanning hundreds of thousands or millions of years, pose significant challenges for dating methods and for understanding the context of potential artifacts. Philosophically, these models challenge foundational assumptions about human uniqueness and the linear progression of civilization. They raise questions about the nature of evidence itself and whether our current scientific paradigms are sufficiently flexible to accommodate radically different narratives of history. The possibility that evidence has been erased, obscured, or remains undiscovered prompts a re-evaluation of the epistemological limits of our knowledge. Moreover, biases rooted in anthropocentrism, the tendency to view humans as the pinnacle of evolution, may hinder open-minded exploration of these hypotheses. Furthermore, the speculative nature of these models often leads to debates about falsifiability and scientific legitimacy. For a hypothesis to be scientifically validated, it must be testable and falsifiable. Yet, the rarity and ambiguity of potential evidence make this a formidable obstacle. Consequently, these challenges underscore the need for rigorous methodologies and open scientific discourse to assess the plausibility of such extraordinary claims. As we consider the prospects of future discoveries, they have the potential either to bolster or undermine these theoretical frameworks. How could future discoveries support or refute these models? Future discoveries hold the potential to critically evaluate the validity of these theoretical frameworks, either reinforcing or challenging the notion that advanced civilizations may have existed long before humans. Advances in technology, such as deep-sea exploration, satellite imaging, and refined radiometric dating, are poised to reveal new evidence that can reshape our understanding of Earth's history. For example, submerged archaeological sites, once thought inaccessible, might surface through high-resolution sonar mapping, potentially uncovering remains of ancient structures or artifacts that predate known civilizations. Similarly, improved dating techniques could identify anomalous layers of material, be it artifacts or biological remnants, that suggest periods of unexpected cultural activity or technological development, thereby lending support to the hypothesis of prior civilizations. Conversely, these technological advancements also serve as tools to refute the hypothesis. The absence of corroborative evidence, despite exhaustive searches, such as a lack of definitive artifacts, structures, or bioindicators, could reinforce the prevailing view that human civilization is unique in its complexity and temporal placement. Critical analysis of new findings will be essential, as they may reveal natural processes like erosion, sedimentation, or tectonic activity that have obscured or destroyed ancient evidence, leading skeptics to argue that the absence of proof is simply a consequence of geological processes rather than the non-existence of prior civilizations. Furthermore, future discoveries may highlight the importance of contextualizing evidence within Earth's dynamic environmental history. For example, a sudden spike in atmospheric anomalies or unusual sediment layers might be linked to catastrophic events, complicating the interpretation of ancient sites. These environmental factors could either mask traces of previous civilizations by erasing or distorting physical remnants, or, alternatively, preserve them in unique conditions that enable their detection across millennia. In essence, ongoing and future research will continue to test the boundaries of our current models, either uncovering compelling evidence that supports the Silurian hypothesis or providing a robust framework to dismiss it. Each discovery will deepen our understanding of Earth's complex past, emphasizing the importance of integrating technological innovation with multidisciplinary scientific inquiry as we explore the possibility of ancient, pre-human civilizations. Climate change and environmental shifts play a pivotal role in shaping the archaeological and geological records that document human history and, potentially, the histories of other ancient civilizations. These processes can both preserve and obliterate evidence, depending on their nature and intensity. On one hand, certain environmental conditions contribute to remarkable preservation. Rapid burial by sediment during flooding events, the formation of anaerobic environments like peat bogs or waterlogged caves, and the encasement within ice or volcanic ash can protect artifacts, structures, and organic materials from decay. For example, the preservation of Ötzi, the Iceman in the Alps, exemplifies how cold, stable environments can safeguard organic remains for thousands of years. Similarly, volcanic ash layers can encapsulate entire settlements, providing a snapshot of ancient life frozen in time. Conversely, dramatic environmental shifts often erase traces of past civilizations. Ice ages, characterized by extensive glaciation, scour landscapes, crush artifacts, and erode coastal settlements due to sea level fluctuations. During glacial periods, rising ice sheets and shifting climates can obliterate surface evidence, leaving only faint geological signatures. Volcanic eruptions, while sometimes preserving evidence through ash deposits, can also devastate entire regions, destroying archaeological sites and burying them beneath layers of lava and ash. Large-scale oceanic changes, such as sea level rises and drops, alter coastlines dramatically, submerging former land-based sites beneath water or exposing previously hidden ones. These environmental dynamics are double-edged. They can serve as natural custodians, preserving ancient sites for millennia, or as relentless agents of erasure, erasing evidence through erosion, sedimentation, or destruction. Understanding these processes is crucial for interpreting the archaeological and geological record. They influence not only what remains, but also how we find and study ancient civilizations. This complex interplay sets the stage for exploring how these natural forces impact the preservation or loss of evidence, leading us to consider the broader effects of ice ages, volcanic activity, and oceanic changes on our understanding of Earth's history. Ice ages, volcanic activity, and oceanic changes have profoundly shaped the archaeological and geological records, often complicating the quest to uncover evidence of ancient civilizations predating humans. These natural forces act both as agents of preservation and as formidable agents of destruction, leaving behind a complex stratigraphy that can obscure or erase traces of past life. During ice ages, vast expanses of land become cloaked in glaciers, which can both preserve and obliterate archaeological sites. As glaciers advance, they engulf landscapes, preserving artifacts within ice, but during retreat, they often erode or displace material, scattering evidence across broad areas. The weight and movement of ice also deform geological strata, distorting the original context of ancient sites and making chronological reconstruction challenging. Conversely, in regions unaffected by glaciation, the lowered sea levels associated with ice ages expose land bridges, such as the Bering Strait, that facilitated migrations but also alter coastal landscapes, impacting archaeological preservation. Volcanic activity introduces another layer of complexity. Eruptions deposit tephra, volcanic ash, that can blanket entire regions in a layer of volcanic material, sometimes rapidly burying settlements and organic remains. This sudden covering can preserve artifacts in remarkable detail, akin to a natural freeze-drying process. But subsequent eruptions or geological shifts can destroy or displace these deposits. Moreover, volcanic landscapes are often reshaped through lava flows and ash buildup, distorting previous geological formations and complicating stratigraphic analysis. Oceanic changes, including sea level fluctuations and tectonic movements, further influence the archaeological record. During periods of high sea levels, coastal sites are submerged, potentially erasing evidence of early settlements that once thrived near shorelines. Conversely, lowered sea levels expose continental shelves, revealing submerged landscapes that could harbor undiscovered artifacts. Additionally, tectonic uplift and subsidence can displace entire regions, affecting the stratigraphic integrity of archaeological layers and causing older sediments to be buried deep beneath newer deposits or to be uplifted above sea level. Collectively, these environmental processes shape a dynamic, often turbulent geological record. They can both preserve and obliterate evidence of ancient civilizations, making the task of uncovering pre-human societies a meticulous and often elusive pursuit. Understanding these influences is essential to interpret the signals buried within Earth's layered history and to consider whether these natural forces might have concealed the remnants of civilizations long lost to time. Could environmental catastrophes have led to the sudden disappearance of pre-human civilizations? Environmental catastrophes have long been suspected as catalysts for abrupt societal collapses, and their potential role in the disappearance of pre-human civilizations warrants careful examination. Unlike gradual societal decline, sudden environmental upheavals, such as massive volcanic eruptions, asteroid impacts, or rapid climate shifts, could induce rapid destabilization, rendering civilizations unable to adapt swiftly enough to survive. Evidence from geological records suggests that such events have periodically punctuated Earth's history, often with catastrophic consequences. For instance, the Younger Dryas event around 900 years ago, characterized by a sudden onset of intense cooling, is thought to have dramatically affected prehistoric human populations. Similarly, large-scale volcanic eruptions, like the Toba supereruption approximately 74,000 years ago, may have caused significant climatic disruptions, leading to population bottlenecks or even the temporary disappearance of advanced societies. These environmental shocks could have obliterated vital food sources, destroyed infrastructure, or caused widespread environmental degradation, effectively erasing traces of civilizations that had once thrived. Moreover, impact events, such as asteroid strikes, could produce immediate, widespread devastation. The Chicxulub impact, linked to the mass extinction of the dinosaurs, exemplifies how extraterrestrial collisions can trigger environmental crises that wipe out entire ecosystems and, consequently, the civilizations dependent upon them. While these events are less frequent, their destructive potential is immense, capable of abruptly ending complex societal organizations. It is also important to consider that environmental catastrophes may not solely wipe out civilizations outright, but could fragment or weaken them to the point where they collapse under subsequent pressures. For example, a sudden climate shift could destabilize agriculture, leading to resource shortages, social upheaval, and eventual abandonment of settlements. In sum, natural environmental catastrophes have the capacity to induce rapid, profound changes in Earth's biosphere and surface conditions. Such upheavals could serve as the ultimate factors behind the sudden disappearance of pre-human civilizations, leaving behind only scant trace evidence that modern scientists continue to piece together. This understanding underscores the importance of studying Earth's geological history to better grasp how fragile and fleeting ancient societies might have been in the face of natural disasters. Natural sedimentation and erosion are fundamental geological processes that significantly influence the preservation or degradation of ancient artifacts. Over millennia, sedimentation, the gradual accumulation of mineral and organic particles, acts as an insulating blanket, often encapsulating artifacts buried beneath the Earth's surface. In stable environments, such as deep lake beds or floodplains, this process can create remarkably well-preserved conditions, shielding artifacts from physical disturbances, chemical degradation, and biological activity. For instance, the rapid burial of tools or organic remains in fine sediments can slow decay, allowing them to survive for tens of thousands of years. Conversely, in dynamic settings where sedimentation rates are slow or irregular, artifacts are more susceptible to exposure and erosion, limiting their chances of preservation. Erosion, on the other hand, acts as both a destructive and revealing force. It gradually wears away layers of soil and sediment, exposing artifacts that had previously been buried or concealed. While erosion can destroy archaeological sites, it also uncovers hidden layers, offering glimpses into ancient human activity otherwise inaccessible. Coastal cliffs, riverbanks, and mountain slopes are particularly notable for these dual roles. They often serve as natural excavations, exposing artifacts that can provide critical insights into prehistoric life. The interplay of sedimentation and erosion also influences the chemical environment surrounding artifacts. Minerals deposited with sediments can create conditions conducive to preservation through mineralization or, alternatively, foster chemical reactions that degrade organic materials. Acidic soils, for example, accelerate the breakdown of bone and wood, whereas neutral or alkaline conditions tend to favor preservation. Understanding these processes is crucial in archaeological interpretation. They not only determine the likelihood of finding well-preserved artifacts, but also affect how evidence is distributed across the landscape. Recognizing the signs of past sedimentation and erosion events can help archaeologists identify promising excavation sites or interpret the context of recovered artifacts. Building on this foundation, it is essential to consider how natural resource deposits, such as mineral-rich layers, may further influence the visibility or concealment of ancient evidence. What role do natural resource deposits play in hiding or revealing evidence of ancient activity? Natural resource deposits serve as both concealment and revelation points for evidence of ancient human activity. These deposits, such as mineral veins, coal seams, and aquifers, interact intricately with the geological and environmental histories of regions, often shaping the visibility of archaeological traces. When humans utilized or altered these resources, they inadvertently left behind subtle signs, artificial modifications in mineral deposits, remnants of mining activities, or disturbed stratigraphy that can be detected through modern scientific techniques. For instance, ancient mining operations, which often targeted accessible mineral deposits, can leave behind distinctive geological signatures. These include altered rock formations, residual slag, or unusual concentrations of certain elements, which can be identified through geochemical analysis. In some cases, these deposits have preserved artifacts or structural remains within their layers, effectively acting as time capsules. Conversely, natural resource deposits can also obscure evidence of past activity. Over geological time, processes like sedimentation, erosion, or mineralization can mask or distort archaeological layers, making it challenging to distinguish between natural formations and human-made modifications. Moreover, resource-rich areas tend to attract early human settlement and activity, but the very processes that make these deposits attractive, such as mineral extraction, can lead to the disturbance or destruction of archaeological sites. Ancient artifacts buried within mineral-rich sediments may be displaced or buried deeper, complicating their detection. Conversely, in some cases, resource deposits can preserve evidence exceptionally well. For example, peat bogs and mineral-rich lakes have been known to preserve organic materials, providing remarkably well-preserved insights into ancient human life. Understanding the complex relationship between resource deposits and archaeological evidence emphasizes the importance of multidisciplinary approaches, combining geology, geochemistry, and archaeology to identify promising sites. Recognizing how natural deposits influence the preservation or concealment of ancient activity is critical in reconstructing our hidden past, especially when considering the possibility that some evidence may be lurking beneath layers we haven't yet fully explored. This line of inquiry naturally leads to considering how climate models might help us predict where such preserved evidence could be found, guiding future archaeological discoveries. Climate models serve as invaluable tools in the quest to locate and interpret evidence of ancient civilizations, offering insights that extend beyond traditional archaeological methods. These models simulate long-term environmental conditions, helping researchers identify regions that may have historically supported human habitation but are now obscured or altered by climate change. For example, by reconstructing past climate scenarios, scientists can pinpoint areas where water sources, fertile lands, or stable settlements might have existed, guiding excavations toward promising sites that might otherwise remain undiscovered. One key application involves analyzing sedimentary records and paleoclimatic data to understand how shifts in climate, such as periods of increased aridity or flooding, have affected surface preservation. Climate models can identify zones where natural processes, like sediment deposition or erosion, have either protected or destroyed archaeological strata over millennia. This understanding allows archaeologists to prioritize locations that likely harbor well-preserved artifacts or structures, especially in regions vulnerable to environmental upheaval. Moreover, climate modeling enhances the interpretation of subsurface and remote sensing data. For instance, predictive algorithms can suggest where ancient human-made features, such as irrigation channels, roads, or dwellings, might be concealed beneath modern landscapes, particularly in areas subject to significant environmental change. This synergy between climate science and remote sensing optimizes resource allocation for field surveys and excavations. Importantly, these models are continually refined using a combination of geological, biological, and climatological data, creating increasingly accurate reconstructions of past environments. Such reconstructions can reveal transient habitats that supported early civilizations during specific climatic windows, emphasizing the importance of understanding climate variability in archaeological contexts. As we deepen our comprehension of how climate has historically influenced human settlement and survival, these models will become even more vital in predicting where evidence of ancient civilizations might be preserved. They open pathways to uncovering hidden chapters of human history, especially in regions where environmental changes have either preserved or erased traces of our ancestors' presence. This pursuit underscores the importance of integrating climate science into archaeological exploration, setting the stage for how future climate change might further shape our ability to uncover and interpret humanity's distant past. Future climate change presents both significant challenges and intriguing opportunities for uncovering the remnants of ancient civilizations. As global temperatures rise, glaciers melt, and sea levels fluctuate, the landscape that once concealed human history may reveal new archaeological sites or distort existing ones. These environmental shifts can accelerate the erosion of surface remains, making some archaeological evidence more accessible, yet simultaneously jeopardize delicate artifacts through increased weathering and biological activity. For example, the rapid retreat of ice in polar and glacial regions could expose well-preserved sites, offering unprecedented insights into past societies. Yet these same areas may also become vulnerable to further degradation once exposed. Moreover, altered precipitation patterns and intensified storms can reshape sedimentation processes, washing away or burying archaeological layers that previously provided vital chronological context. In some cases, floods and landslides may obliterate entire sites, making it more difficult to piece together ancient histories. Conversely, in arid regions, increased aridity might lead to the preservation of organic materials that would otherwise decay in more humid conditions, potentially expanding the range of discoverable artifacts. The implications extend beyond physical preservation. As climate change impacts the stability of current environments, it influences the likelihood of discovering evidence of ancient civilizations. Regions once thought to be unpromising for archaeology, such as deserts or tundra, might become more accessible or better preserved due to environmental shifts. However, these same changes can also introduce new complexities, such as increased soil salinity or permafrost melt, which can hinder excavation efforts or damage artifacts. Furthermore, the ongoing transformation of landscapes underscores the importance of proactive archaeological research and preservation strategies. As climate change continues to rewrite the Earth's surface, scientists must adapt their methods to identify, document, and conserve ancient remains before they are lost to the changing environment. This dynamic interplay between climate and archaeology highlights how future environmental changes could both reveal and threaten our understanding of human history, emphasizing the urgency of integrating climate considerations into the search for ancient civilizations. The study of past environmental changes offers profound insights into the resilience and vulnerabilities of civilizations over time. Ancient societies, from the Maya to Mesopotamians, faced climate fluctuations, resource depletion, and natural disasters that often precipitated societal decline or transformation. These historical episodes serve as critical lessons, emphasizing that no civilization is immune to environmental pressures, regardless of technological advancement or societal complexity. One key lesson is the importance of adaptability. Civilizations that thrived often demonstrated an ability to modify their agricultural practices, manage resources sustainably, or shift their societal structures in response to environmental shifts. Conversely, societies that failed to recognize or respond effectively to ecological signals, such as prolonged droughts or soil degradation, tended to decline. For example, the collapse of the classic Maya civilization correlates with evidence of climate variability and deforestation, underscoring how environmental stressors can compound societal vulnerabilities. Another vital lesson is the necessity of long-term planning and environmental stewardship. Many ancient civilizations lacked the foresight or institutional capacity to mitigate impending ecological crises, leading to resource exhaustion and social upheaval. Modern parallels emerge in our ongoing challenges with climate change, where the depletion of fossil fuels, deforestation, and pollution threaten the stability of contemporary societies. Recognizing the patterns in historical collapses underscores the importance of sustainable practices and proactive resilience building. Furthermore, the archaeological record reveals that environmental disruptions can catalyze cultural and technological innovation. Societies often respond to crises by developing new technologies, social strategies, or religious paradigms to cope with changing conditions. These adaptive responses highlight human ingenuity and the capacity for renewal, even amid adversity. In sum, examining past environmental changes underscores that the longevity of civilizations hinges on their ability to adapt, plan, and respect ecological limits. This historical perspective not only informs our understanding of societal resilience, but also serves as a cautionary tale for current and future civilizations. It invites us to consider how environmental stewardship is integral to sustaining human civilization, fostering a deeper appreciation for the delicate balance between society and nature. As we reflect on these lessons, the question naturally arises: how does the search for extraterrestrial intelligence, SETI, relate to the hypothesis of ancient civilizations on Earth? The search for extraterrestrial intelligence, SETI, extends beyond merely attempting to contact distant civilizations. It also encompasses the intriguing possibility that evidence of ancient extraterrestrial presence might already be embedded within our cosmic environment. This perspective aligns with the Silurian Hypothesis, which posits that advanced civilizations could have existed long before humans and potentially left behind detectable traces. Therefore, SETI's scope broadens from listening for ephemeral signals to seeking tangible artifacts or anomalies that suggest past extraterrestrial activity. Traditional SETI efforts primarily focus on detecting electromagnetic signals, radio waves, or laser pulses that might be intentionally transmitted by intelligent beings. However, if extraterrestrial civilizations experienced rise and fall eons ago, their communications could have ceased long before humanity's technological era, making active signal detection insufficient. Instead, scientists increasingly consider the possibility that relics of these civilizations might be observable in the form of astroarchaeological artifacts, structures, modifications, or unusual phenomena on celestial bodies or within the interstellar medium. One avenue of inquiry involves examining planetary surfaces and moons for signs of artificial modification. For instance, unusual surface features, geometric formations, or anomalous energy signatures could hint at past construction or resource extraction activities. Likewise, the detection of non-natural mineral deposits or large-scale excavation sites might suggest ancient industrial activity. These remnants could be preserved on planetary scales, offering clues about civilizations that predated us by millions or billions of years. Beyond planetary surfaces, SETI researchers also explore the possibility of detecting technosignatures, indirect indicators of technological activity embedded in the cosmic environment. These could include unusual patterns in the distribution of cosmic dust, anomalous energy emissions, or even modifications to natural astrophysical phenomena. For example, Dyson spheres or swarms, hypothetical megastructures designed to harness stellar energy, could, if constructed eons ago, still cast detectable signatures. Furthermore, the search extends into the realm of artifacts or signals originating from space-based objects, such as artificial satellites or probes, that might have drifted into our solar system or beyond. If civilizations engaged in interstellar exploration or colonization, remnants of their endeavors could be scattered across the galaxy, waiting to be discovered as silent witnesses to their existence. In essence, the quest to identify ancient extraterrestrial civilizations involves a multifaceted approach, combining traditional SETI methods with innovative searches for relics, artifacts, structures, and signals that could reveal a long-lost cosmic history. This expands the scope of SETI from active communication to a profound archaeological investigation across the universe. Detecting signals or artifacts from space that could point to ancient extraterrestrial civilizations requires a nuanced understanding of both astrophysical phenomena and the potential signatures such civilizations might leave behind. Unlike the rapid, high-energy signals often associated with modern technological activity, ancient extraterrestrial artifacts would likely be subtle, preserved over millions of years within cosmic or planetary environments. One of the primary indicators scientists consider is anomalous electromagnetic signals emanating from specific regions of space. While current SETI efforts focus on detecting intentional signals, beacons, or communication attempts, ancient civilizations might have produced more passive signatures. For example, the presence of unusual radio or laser emissions that do not fit natural astrophysical sources could hint at past technological activity. These signals might be weak, sporadic, or embedded within the cosmic background, requiring sophisticated analysis to distinguish them from natural phenomena like pulsars or quasars. Another potential artifact is the discovery of unusual physical structures or anomalies in celestial bodies. For instance, large, geometrically precise formations on the surfaces of asteroids, moons, or even planets, reminiscent of megastructures, could be indicative of past engineering. Such structures might have been built for resource extraction, habitat, or scientific purposes, and could remain as silent witnesses of ancient activity. Detecting these requires high-resolution imaging and remote sensing technologies capable of uncovering subtle irregularities beneath planetary surfaces or within asteroid debris. Additionally, the spectral analysis of cosmic dust and meteorites offers a promising avenue. Unusual isotopic ratios or the presence of anomalous materials, non-natural compounds or metals could suggest extraterrestrial manufacture. These artifacts might have originated from manufacturing processes or spacefaring activities subsequently delivered to Earth via meteorites or cosmic debris. While these signals and artifacts are challenging to identify, advances in astronomical instrumentation, data processing, and interdisciplinary approaches are steadily enhancing our ability to recognize the faint traces of ancient civilizations. Yet, the question remains, could some of these extraterrestrial signatures be hidden deep within the fabric of our own planet's geological or archaeological record? Extraterrestrial artifacts, if present within Earth's geological or archaeological record, could fundamentally challenge our understanding of human history. Unlike typical artifacts created by human hands, such objects might exhibit technological or material properties that seem inexplicable within the context of known ancient civilizations. For example, anomalies such as unusually advanced metallurgy, materials with isotopic signatures inconsistent with terrestrial processes, or structures that defy conventional construction techniques could signal extraterrestrial origins. These artifacts might be embedded deep within strata associated with ancient geological events, or they could be subtly incorporated into artifacts long thought to be purely human-made. Detecting such anomalies requires careful analysis and a multidisciplinary approach. Geochemists could identify unusual isotopic ratios suggestive of extraterrestrial sources, while materials scientists might uncover inexplicable alloys or composites. In some cases, meteorite fragments or unusual mineral formations embedded in ancient sediments could be mistaken for natural phenomena unless thoroughly studied. Archaeologists, meanwhile, must remain open to the possibility that certain enigmatic objects, such as unexplained carvings, symbols, or artifacts with no clear cultural affiliation, may have extraterrestrial origins. A significant challenge lies in distinguishing genuine extraterrestrial artifacts from rare natural occurrences or misinterpretations of ancient craftsmanship. The presence of unusual artifacts in archaeological sites can easily be dismissed as natural anomalies or modern contamination unless backed by rigorous scientific validation. Moreover, the scarcity of such artifacts and the difficulty in dating them precisely complicate efforts to establish their extraterrestrial provenance conclusively. The idea that extraterrestrial objects might be hidden or integrated into Earth's ancient record invites a re-examination of archaeological findings that have long been considered ambiguous. Such a perspective encourages scientists and researchers to expand their investigative frameworks, incorporating astrobiological and planetary science insights. This approach opens up the possibility that Earth's history is more intertwined with cosmic visitors than previously assumed, setting the stage for intriguing debates about how we interpret the unexplained relics of our distant past. As we consider these possibilities, it becomes natural to question how ancient alien theories could shape our understanding of ambiguous archaeological discoveries. Ancient alien theories often challenge conventional archaeological interpretations by suggesting that extraterrestrial beings may have influenced or even seeded early human civilizations. This perspective encourages researchers to re-examine ambiguous findings, unusual artifacts, inexplicable structures, or anomalous markings through a broader lens that considers non-human origins. Instead of dismissing these anomalies as mere natural phenomena or cultural coincidences, proponents argue they might be remnants of alien contact or intervention. For example, strange carvings or symbols that defy cultural progression could be viewed as artifacts left by advanced extraterrestrial visitors, perhaps serving as messages or symbols whose meaning has been lost over millennia. This reinterpretation prompts a critical reassessment of archaeological contexts, urging scholars to question the assumption that all ancient artifacts are purely human-made. It opens the door to alternative explanations where extraterrestrial influence is considered a viable factor. especially when findings appear inconsistent with known technological or cultural capabilities of ancient societies. Such perspectives foster interdisciplinary collaborations, integrating fields like astronomy, geology, and materials science to analyze anomalies. The possibility that some artifacts or materials might have extraterrestrial origins or connections compels researchers to consider non-traditional sources of evidence, encouraging open-mindedness and innovation in investigative methods. Furthermore, ancient alien hypotheses influence the search for extraterrestrial artifacts by broadening the scope of inquiry beyond traditional excavation sites. Researchers might explore cosmic phenomena or extraterrestrial debris that could harbor clues or physical remnants of ancient civilizations. This leads naturally to considering how extraterrestrial materials, like meteorites and cosmic dust, could serve as carriers of evidence. These cosmic materials, which constantly rain down on Earth, may contain embedded information, biosignatures, or even physical artifacts from distant worlds or ancient civilizations that once interacted with extraterrestrial visitors. Exploring this possibility requires an understanding of how cosmic debris interacts with Earth's environment and how it might preserve or transmit clues about ancient life or civilizations beyond our planet. Meteorites and cosmic dust are more than mere remnants of cosmic events. They serve as potential messengers, carrying clues about ancient civilizations beyond Earth. Their role in the search for extraterrestrial artifacts hinges on their ability to transport material and perhaps even biological or technological signatures across vast interdistances. As these celestial particles traverse space, they can encapsulate fragments of planetary surfaces, technological debris, or other anomalous materials that originated from civilizations long lost or hidden on distant worlds. Meteorites, in particular, are invaluable in this context because they originate from planetary bodies and retain chemical and isotopic signatures unique to their source environments. When a meteorite lands on Earth, it can contain isotopic anomalies or embedded microstructures that hint at artificial origins or past technological activity. For example, certain isotopic ratios of elements like nitrogen or noble gases could signify processes not naturally occurring in planetary geology, raising the possibility of artificial manipulation. Additionally, some meteorites have shown structures that resemble microfabricated or machine-like features, sparking speculation about their artificial origin. Cosmic dust, composed of microscopic particles from comets, asteroids, and interstellar clouds, offers a subtler but equally intriguing avenue for investigation. These tiny particles can carry complex organic molecules, unusual mineral phases, or other chemical signatures that may be linked to biological or technological activity. Because cosmic dust accumulates in planetary atmospheres and can be collected and analyzed, it provides a continuous record of material from diverse regions of space. Anomalies or unusual compounds found within this dust could serve as indirect evidence of extraterrestrial activity, especially if they deviate from natural formation patterns. Furthermore, advances in analytical techniques such as high-precision mass spectrometry, electron microscopy, and spectroscopy enable scientists to detect minute anomalies within meteorites and cosmic dust. These methods can reveal chemical, isotopic, or structural markers that might otherwise go unnoticed, offering tantalizing hints of ancient civilizations' presence or their remnants carried across space. As research progresses, this cosmic cargo could unveil hidden chapters of cosmic history, illuminating possible interactions between ancient civilizations and the universe at large. Astronomical observations serve as a crucial tool in the quest to identify potential regions where ancient terrestrial artifacts might reside, especially within the context of the Silurian Hypothesis. These observations extend beyond mere visual surveys to encompass a multifaceted analysis of celestial phenomena, stellar environments, and cosmic anomalies that could hint at past extraterrestrial activity. One pivotal approach involves examining regions around ancient stars and planetary systems for unusual features or irregularities that deviate from natural astrophysical processes. For example, anomalies such as unexplained dimming patterns in stars, like the mysterious behavior observed in KIC 8,462,852, also known as Tabby's star, have prompted speculations about the presence of megastructures or other artificial constructs. Infrared telescopes, such as the Wide Field Infrared Survey Explorer, WISE, play a significant role by detecting excess infrared radiation that might indicate large-scale energy harvesting structures like Dyson spheres. These hypothetical constructs, designed to encompass a star to capture its energy, would emit characteristic infrared signatures distinguishable from natural phenomena. Consequently, astronomers analyze data for such anomalies, seeking patterns inconsistent with known astrophysical objects. Similarly, radio telescopes like the Allen Telescope Array enable the search for anomalous signals, narrowband, patterned emissions that could originate from technologically advanced civilizations or remnants thereof. Furthermore, the study of planetary surfaces and their atmospheres through spectroscopy can reveal unusual compositions or surface features that may be indicative of artificial modification or artifact deposition. For instance, detecting materials or structures that do not naturally form under known geological or atmospheric conditions could provide indirect evidence of past extraterrestrial activity. Additionally, the distribution of objects in the Kuiper Belt or Oort cloud, observed through precise telescopic surveys, might uncover debris fields or structures that seem out of place or too orderly to be purely natural. Collectively, these astronomical techniques form a comprehensive toolkit for pinpointing promising locations where artifacts might exist. They allow scientists to narrow down vast regions of space to specific targets for more detailed investigation. However, despite the sophistication of these methods, the endeavor remains fraught with challenges, particularly in distinguishing artifacts of intelligent origin from natural cosmic phenomena, a task that demands not only advanced technology but also careful interpretation of ambiguous signals. Distinguishing natural cosmic phenomena from artificial signals presents a formidable scientific challenge, primarily because the universe is replete with a diverse array of energetic emissions and transient events that can easily mimic signs of intelligent origin. At the heart of this difficulty lies the ambiguity inherent in many astrophysical signals. For example, fast radio bursts, FRBs, which are intense, millisecond duration flashes of radio waves, can resemble potential communication signals but are widely believed to originate from highly energetic astrophysical processes such as neutron star collisions or magnetar activity. Differentiating these natural origins from artificial sources requires meticulous analysis of their properties, including spectral characteristics, temporal patterns, polarization, and repetition rates. A major obstacle is the sheer diversity and unpredictability of natural phenomena. Many cosmic signals are transient, unpredictable, and often lack the repetitive patterns that would suggest an intentional transmission. For instance, pulsars, rotating neutron stars emitting periodic radio pulses, can be mistaken for potential extraterrestrial beacons, yet their highly regular emissions are well characterized with known physical models. Conversely, signals with irregular or non-repeating features raise suspicion but could still stem from complex natural processes. This ambiguity complicates efforts to classify signals confidently, especially when data is limited or noisy. Another challenge involves the technological limitations of our current detection methods. Radio telescopes and signal processing algorithms are continually advancing, yet they may still lack the sensitivity or resolution necessary to distinguish subtle signs of artificiality. Interference from human-made sources, satellites, terrestrial radio signals, or space debris further complicates the identification process, often producing false positives that mimic extraterrestrial signals. Moreover, the possibility that extraterrestrial civilizations might employ communication methods vastly different from human technologies introduces additional complexity. If advanced civilizations use signals outside our current detection capabilities, such as laser pulses, neutrino emissions, or other exotic means, our tools might not even recognize these signals as artificial. In essence, the challenge is not just technical but conceptual. Understanding what constitutes a meaningful signature of intelligence amid the vast cosmic background. As our observational techniques improve and theoretical models evolve, scientists inch closer to distinguishing natural cosmic phenomena from potential signs of extraterrestrial technology, a pursuit that remains at the frontier of astrophysics and SETI research. Future space missions hold the tantalizing potential to uncover evidence of ancient civilizations beyond Earth, fundamentally expanding our understanding of life's history in the universe. Advances in technology, such as more sensitive spectrometers, robotic explorers, and advanced remote sensing, are poised to revolutionize our ability to detect signs of past or present extraterrestrial intelligence. Missions targeting moons like Europa and Enceladus, which harbor subsurface oceans, could uncover biosignatures or even technosignatures, indicators of technological activity that point to ancient civilizations once thriving beneath icy surfaces. Similarly, Mars missions continue to seek traces of past life, with a focus on fossilized microorganisms preserved in ancient sediments. The discovery of complex organic molecules or other bioindicators would suggest that life, and perhaps civilization, has arisen independently on other planets. Beyond our solar system, telescopic observations are increasingly capable of analyzing exoplanet atmospheres for chemical anomalies, such as industrial pollutants or artificial light, that might hint at past technological activity. The detection of such signatures would be a watershed moment, hinting that intelligent societies could have existed elsewhere and left behind detectable traces. Furthermore, the search for extraterrestrial artifacts, like alien megastructures or anomalous radio signals, remains a core component of future exploration strategies. As our detection methods improve, the possibility of identifying remnants of ancient civilizations, whether through structural remains or residual energy signatures, becomes less speculative. These efforts could reveal civilizations that flourished millions or even billions of years ago, their remnants preserved through cosmic timescales. However, the challenge lies in distinguishing true evidence of civilization from natural phenomena or false positives. The development of rigorous criteria and interdisciplinary approaches will be crucial to interpret any findings reliably. The prospect of uncovering ancient extraterrestrial civilizations would not only answer profound questions about life's ubiquity, but also reshape our understanding of our place in the cosmos. It would prompt us to consider whether humanity is unique or merely one chapter in a vast, ongoing narrative of cosmic civilization, an inquiry that inevitably leads us to question the very origins of human life itself. The discovery of evidence pointing to pre-human civilizations would fundamentally transform our understanding of human origins, prompting a seismic shift in scientific, philosophical, and societal paradigms. Traditionally, human evolution has been viewed as a linear progression culminating in modern Homo sapiens, with a clear chronological narrative supported by fossil records, genetic studies, and archaeological findings. However, uncovering traces of civilizations predating humans would challenge this linear perspective, suggesting that intelligent life, and perhaps complex societies, existed long before our species emerged. Such evidence would imply that humans are not the sole or even the earliest architects of civilization. Instead, it would force us to reconsider the uniqueness of human intelligence and technological development, opening questions about the conditions necessary for societal complexity. Were these ancient civilizations technologically advanced, or did they possess forms of knowledge and organization that surpass our current understanding? The possibility that prior civilizations might have risen and fallen, leaving behind subtle or long-buried remnants, would also reshape our grasp of societal resilience and vulnerability across planetary history. Furthermore, this revelation would challenge the anthropocentric view of progress, prompting a reassessment of humanity's place within Earth's long history. It would suggest that our species might be a latecomer in a broader narrative of life and intelligence, fundamentally altering how we interpret our evolutionary trajectory. The implications extend beyond science, touching on questions of purpose and destiny. If civilizations can rise, fall, and perhaps be forgotten, what does that say about the potential longevity and sustainability of human society? Moreover, the discovery would resonate deeply within the realms of philosophy and cultural identity. It could inspire humbling reflections on our assumptions of uniqueness, prompting us to reconsider notions of progress and the meaning of consciousness. Ultimately, the potential existence of ancient, pre-human civilizations invites us to view our history not as a singular story, but as part of a more intricate, possibly cyclical, saga of cosmic and terrestrial evolution, one that continually challenges and expands our understanding of life itself. The revelation that humans are neither the first nor the sole intelligent species to have existed fundamentally challenges our most cherished philosophical and cultural paradigms. Such a discovery would force us to confront profound questions about our place in the universe, the uniqueness of human consciousness, and the nature of progress itself. Traditionally, many cultures and philosophies have viewed humanity as a pinnacle of creation, a species with a special, perhaps divine, role in the cosmic order. Recognizing the existence of previous or concurrent intelligent civilizations would dismantle this anthropocentric worldview, compelling us to consider a universe teeming with consciousness and innovation over countless epochs. Culturally, this shift could lead to a re-evaluation of human exceptionalism. Myths, religious doctrines, and philosophical doctrines that emphasize human uniqueness might be challenged or reinterpreted within a broader cosmic context. The idea that humanity is a singular, isolated ascent toward enlightenment would give way to a narrative emphasizing continuity, cyclicity, and perhaps even a shared cosmic heritage among multiple intelligent species. Such a perspective could foster humility, encouraging a sense of kinship with other potential intelligences, whether past or future. Philosophically, the implications extend into questions about identity, purpose, and morality. If prior civilizations had achieved levels of technological or societal sophistication, their rise and fall might offer lessons and warnings about the trajectory of our own development. The recognition that intelligent life can emerge, flourish, and decline multiple times in Earth's history would prompt a re-evaluation of our assumptions about stability and progress. It might inspire us to consider whether technological advancement is an inevitable or cyclical process, or if it is subject to environmental or cosmic constraints that transcend individual civilizations. Furthermore, the uncertainty surrounding such discoveries would deepen existential debates. Are we truly the first in some cosmic sense, or merely the latest iteration in a long continuum of intelligent life? This ambiguity could spark a renaissance of philosophical inquiry, inspiring new ways to think about consciousness, legacy, and the potential for future civilizations. Ultimately, uncovering evidence of other intelligent species would not only reshape our scientific understanding, but also profoundly influence our self-perception and cultural narratives about humanity's role in the universe. Discovering evidence of ancient pre-human civilizations would profoundly reshape our understanding of technological progress and societal development. Traditionally, human history has been viewed as a linear trajectory, marked by incremental advancements, from rudimentary tools to complex societies. However, evidence of prior civilizations would challenge this paradigm, suggesting that technological evolution may not be solely a human endeavor, but part of a broader, possibly cyclical pattern of societal rise and fall across planetary history. If we were to find remnants of highly developed ancient societies, our assumptions about the pace and nature of progress would need re-evaluation. For instance, the existence of advanced infrastructure or artificial modifications on a geological scale could imply that societies once achieved technological heights comparable to, or even surpassing, our current state. Such discoveries would prompt us to question whether technological innovation is an inherent trait of intelligent life or contingent upon specific environmental and societal conditions. Furthermore, this could suggest that civilizations may undergo phases of rapid advancement followed by catastrophic decline, a pattern potentially repeating over geological timescales. Understanding that multiple civilizations could have existed at different points in Earth's history would also influence how we interpret societal development. It might indicate that technological progress is not necessarily linear or cumulative, but subject to complex variables, including environmental changes, resource depletion, or societal collapse, that reset the trajectory. This insight could foster humility about our own developmental path, emphasizing resilience and adaptability in societal evolution. Moreover, such discoveries would impact our perspective on the sustainability of technological growth. Recognizing that advanced civilizations may have faced their own challenges and collapses could serve as a cautionary tale, urging us to consider the long-term viability of our current trajectory. It might also inspire a reassessment of what constitutes progress, shifting focus from mere technological achievement to societal resilience and ecological harmony. As these revelations reshape our understanding of progress, they inevitably lead us to question the ethical implications of uncovering and interpreting evidence of ancient civilizations. How we approach this knowledge, whether with reverence, curiosity, or caution, becomes a vital consideration, setting the stage for deeper reflection on our place within Earth's complex history. The pursuit of uncovering evidence of ancient civilizations beyond human history raises profound ethical considerations that extend beyond scientific curiosity. As researchers delve into the depths of geological and biological records, they must grapple with questions of stewardship, respect, and potential consequences of revelation. Foremost among these concerns is the issue of cultural and societal impact. Revealing evidence of a pre-human civilization could challenge deeply held beliefs, religious doctrines, and cultural identities, potentially causing upheaval or distress within communities. Responsible dissemination of such findings requires careful communication, emphasizing scientific rigor and acknowledging uncertainties to prevent misinformation or unwarranted speculation. Furthermore, there is the question of preservation and disturbance. The act of excavating or probing ancient geological layers might inadvertently damage delicate environments or fragile evidence. Scientists and policymakers must weigh the benefits of discovery against the risks of disrupting preserved records, which serve as invaluable archives of Earth's history. Ethical research mandates minimal invasive procedures, ensuring that investigations do not compromise the integrity of the very evidence they seek. Another layer of complexity involves the potential geopolitical implications. Discoveries that suggest advanced ancient civilizations could challenge national narratives or claims of cultural primacy. This raises concerns about the misuse of evidence for political or ideological purposes, underscoring the importance of international cooperation and transparent, peer-reviewed research processes. Establishing shared guidelines and respecting the sovereignty of archaeological sites can help mitigate conflicts and promote responsible exploration. Finally, the possibility of revealing ancient civilizations prompts us to consider the moral responsibilities toward future generations. Deciding what to preserve, how to interpret ambiguous evidence, and whether to disclose sensitive findings all demand careful ethical deliberation. Researchers must balance the pursuit of knowledge with mindfulness of the societal and environmental impacts, ensuring that the quest to understand our distant past honors both scientific integrity and ethical duty. As scientific techniques evolve, these considerations will become increasingly vital in guiding responsible exploration of Earth's deep history. Future scientific advancements hold tremendous potential to revolutionize our capacity to detect and interpret evidence of ancient civilizations, especially those predating human existence. As our technological toolkit expands, so too does our ability to uncover subtle signatures embedded deep within Earth's geological and environmental records. For instance, Advances in high-resolution isotope analysis could enable scientists to identify anomalous chemical signatures indicative of large-scale industrial activity or technological processes that are otherwise indistinguishable from ADD, natural phenomena. Similarly, improvements in microscopic imaging techniques, such as enhanced electron microscopes or synchrotron radiation methods, may reveal microstructures or nanomaterials like specific ceramics, metals, or composite materials that point toward artificial origins. Emerging fields like astrochronology and geophysical imaging promise to refine our understanding of Earth's deep past. Enhanced seismic surveys, coupled with machine learning algorithms, could detect buried structures or artifacts that challenge existing geological assumptions about the timing and nature of past civilizations. These technologies can help differentiate between natural geological formations and potential remnants of non-human activity, even in regions previously considered inhospitable or devoid of such evidence. Furthermore, advancements in computational power and data analytics will facilitate comprehensive analysis of vast datasets, enabling pattern recognition at scales previously unattainable. This could lead to the identification of subtle, widespread markers of technological activity, such as global dispersal of specific isotopic signatures or anomalous distributions of certain minerals linked to ancient civilizations. The integration of climate modeling and paleo-environmental data will also enhance our understanding of how ancient societies interacted with their environment, revealing indirect evidence of their existence and impact. As we push the boundaries of detection, these innovations will not only improve the sensitivity and specificity of our searches, but will also deepen our interpretative frameworks. The ability to more precisely date findings and assess their context within Earth's history will be crucial in distinguishing artificial signals from natural processes. Ultimately, these advancements will steadily transform speculative hypotheses into scientifically grounded narratives, bringing us closer to uncovering the true scope and complexity of Earth's ancient past. Interdisciplinary research is fundamental to advancing the search for ancient civilizations, especially when exploring hypotheses like the Silurian Hypothesis that challenge conventional scientific paradigms. At its core, this approach synthesizes insights from diverse fields: geology, paleontology, archaeology, climatology, astrophysics, and even genetics, to construct a comprehensive understanding of Earth's deep past. Geologists and paleontologists contribute crucial data on ancient sediment layers, isotopic signatures, and fossil records that may harbor clues of past technological activity or environmental disturbances caused by civilizations long before humans. Archaeologists, on the other hand, develop innovative methods for detecting subtle artifacts or structural anomalies buried deep within geological strata, often applying cutting-edge imaging technologies like ground-penetrating radar or remote sensing. Climatologists help interpret ancient climate patterns and environmental shifts that could have influenced the rise or fall of early civilizations, while astrophysicists consider cosmic events, such as asteroid impacts or solar anomalies, that might have left telltale marks in geological records. Geneticists can analyze ancient DNA remnants to reconstruct biological histories, potentially uncovering evidence of domesticated plants or animals associated with early technological societies. Moreover, interdisciplinary collaboration fosters the development of novel methodologies, like integrating geochemical analyses with advanced modeling techniques to distinguish between natural phenomena and potentially artificial alterations in the geological record. Cross-disciplinary dialogue encourages the questioning of assumptions, prompting researchers to consider unconventional explanations and to refine hypotheses with a multidimensional perspective. This collaborative synergy not only broadens the scope of investigation, but also enhances the robustness of findings, reducing the risk of oversight or misinterpretation. As the search for evidence of ancient civilizations gains momentum, the integration of diverse scientific expertise becomes indispensable, ensuring that emerging data is interpreted within a rich contextual framework. In essence, interdisciplinary research acts as a vital catalyst, uniting disparate scientific disciplines to piece together the complex puzzle of Earth's ancient history. This holistic approach increases the likelihood of uncovering subtle signals of long-lost civilizations, thereby expanding our understanding of the planet's true history and the potential for civilizations predating our own. Confirmation of ancient civilizations would profoundly influence our approach to planetary protection and preservation, reshaping our understanding of Earth's resilience and vulnerability. Recognizing that complex life and potentially technologically advanced societies existed long before humans would underscore the importance of safeguarding the planet's deep history, not merely its current state. Such acknowledgement would drive a paradigm shift from a narrow focus on superficial environmental conservation to a more comprehensive stewardship that considers the long-term integrity of Earth's geological and ecological record. One immediate implication would be a heightened emphasis on preserving geological archives, rock strata, fossil records, and sediment layers that serve as repositories of ancient civilizations' footprints. Protecting these layers from contamination or destruction would become a priority, as they could contain invaluable clues to understanding past planetary disturbances, climate shifts, and biosphere resilience. This, in turn, would foster the development of advanced monitoring technologies aimed at detecting subtle changes or disturbances that could threaten these ancient records. Furthermore, the realization that civilizations may have previously altered Earth's environment significantly would prompt a re-evaluation of planetary resilience. It might reveal that Earth's systems are more adaptable than previously assumed, or conversely, more fragile when faced with sustained impacts, whether from natural events or human activity. Consequently, future planetary protection policies would need to incorporate lessons from these ancient episodes, emphasizing preventative measures against irreversible damage and promoting sustainable interaction with Earth systems. In addition, acknowledging ancient civilizations could catalyze international efforts to establish global standards for planetary preservation, akin to space treaties that regulate extraterrestrial exploration. This broader perspective might foster cooperation aimed at minimizing environmental disruptions that could erase vital geological and archaeological records. It would also encourage investments in interdisciplinary research, blending geology, archaeology, and climate science to better understand Earth's historical resilience and vulnerabilities. Ultimately, confirming that Earth once hosted advanced civilizations would deepen our sense of stewardship. It would reinforce the imperative to protect not just the environment, but the very historical fabric of our planet, ensuring that future generations can learn from its ancient past while maintaining its capacity for life and complexity. Understanding our planet's deep history offers profound societal and technological benefits that extend well beyond academic curiosity. By uncovering evidence of ancient civilizations, whether truly pre-human or transient biological communities, we gain invaluable insights into the resilience, adaptability, and ingenuity of life on Earth. These insights can significantly influence our approach to contemporary challenges, from environmental management to technological innovation. Firstly, studying deep-time civilizations enhances our understanding of long-term planetary processes, such as climate change, tectonic shifts, and atmospheric evolution. Recognizing how past environments responded to natural stresses informs models predicting future climate trajectories, equipping us to develop more effective strategies for sustainability. For example, evidence of ancient climate resilience may inspire innovative engineering solutions that mimic natural adaptation mechanisms. Additionally, understanding the technological capabilities of past civilizations, if any, can shed light on the evolution of complex systems and technological innovation. Discovering that ancient societies developed sustainable resource management or energy harnessing techniques could inspire modern solutions to our energy and resource crises. Such knowledge challenges assumptions about technological progress being solely a recent phenomenon and encourages a broader perspective on the potential longevity and adaptability of technological systems. Furthermore, exploring Earth's deep history fosters a sense of humility and interconnectedness among societies. Recognizing that advanced civilizations may have existed long before ours underscores the transient nature of technological dominance and the importance of resilient, adaptable communities. This perspective can influence societal values, promoting sustainable development and long-term thinking rather than short-term gains. On a practical level, the methodologies developed to detect and analyze ancient evidence, such as advanced geochronology, remote sensing, and data modeling, drive technological advancements that benefit multiple disciplines. These innovations often spill over into fields like resource exploration, environmental monitoring, and even space exploration. Ultimately, delving into Earth's deep past enriches our scientific understanding, fuels technological progress, and cultivates a mindset geared towards sustainability and resilience. As we continue to explore the hidden chapters of our planet's history, we not only uncover the secrets of ancient civilizations, but also pave the way for a more informed and adaptable future. Detecting evidence of ancient civilizations poses formidable scientific and technological challenges, rooted in both the nature of geological processes and current limitations of our investigative tools. Unlike archaeological sites from recent human history, where artifacts and structures are relatively accessible, evidence of pre-human civilizations, especially those from hundreds of millions of years ago, is vastly more elusive. One primary obstacle lies in the degradation and recycling of materials over geological timescales. Earth's dynamic crust continually renews itself through tectonic activity, erosion, and sedimentation, often obliterating or dispersing potential signs of ancient technological activity. Furthermore, the signatures we seek, such as anomalous chemical markers, artificial isotopic ratios, or unusual material deposits, are often subtle and difficult to distinguish from natural geological phenomena. For example, certain industrial byproducts or synthetic compounds produced by hypothetical ancient civilizations might resemble naturally occurring substances, making it challenging to identify them conclusively. Advanced detection methods, such as high-resolution spectroscopy or deep earth drilling, are necessary but often limited by technical feasibility, cost, and the sheer scale of the search area. Another significant challenge is the temporal resolution of our geological records. Many potential markers of ancient civilizations could have been erased or deeply buried over millions of years. The Earth's surface is a constantly changing environment with processes that can dilute or destroy evidence, such as volcanic activity, subduction, or sediment compaction, making it difficult to find unambiguous traces. Additionally, the temporal gap between the existence of such civilizations and our current state means that any evidence has likely undergone extensive alteration, complicating efforts to interpret it accurately. Finally, our understanding of Earth's deep history remains incomplete. The further back we look, the less detailed our records become, and the more we must rely on indirect evidence or assumptions. This uncertainty underscores the importance of developing innovative technologies and interdisciplinary approaches, combining geology, chemistry, and even astrobiology to improve our chances of uncovering the faint echoes of civilizations long vanished beneath the Earth's surface. The vast timescale of Earth's history, spanning over 4.5 billion years, poses a formidable obstacle in the search for evidence of ancient civilizations, especially those predating humans. This immense temporal expanse means that any potential markers of early technological activity are subject to a relentless process of geological transformation, obscuring or erasing their traces over eons. Unlike archaeological sites that can be excavated and directly studied, ancient technological signatures embedded within the Earth's crust must endure natural forces such as tectonic shifts, erosion, sedimentation, and chemical alterations. These processes can significantly alter or obliterate evidence, making it exceedingly difficult to distinguish between natural and artificial origins. Furthermore, the sheer duration introduces a fundamental challenge. The accumulation of geological records is inherently incomplete. The Earth's crust is constantly renewed and recycled through plate tectonics, subduction, and volcanic activity, which can erase entire layers or distort the context of any surviving artifacts. As a result, the preservation of physical evidence, such as remnants of machinery or construction materials, is exceedingly rare and often fragmented. This scarcity hampers efforts to establish definitive timelines or identify specific technological signatures, especially when their original forms may have been reduced to indistinct mineral deposits. Compounding this difficulty is the slow pace of geological processes that transform and integrate ancient materials into the broader Earth system. For example, if a civilization's technological artifacts were composed of materials susceptible to chemical weathering, their signals could be masked or indistinguishable from natural mineral deposits after hundreds of millions of years. Similarly, isotopic signatures indicative of artificial manipulation may become indistinct over geological timescales due to diffusion and mixing within Earth's dynamic interior. Consequently, the enormous timescale imposes significant limitations on our ability to detect and interpret evidence of ancient civilizations. It challenges scientists to develop ever more sensitive and sophisticated techniques capable of discerning subtle anomalies within the deep geological record. Yet, the profound span of geological history remains a fundamental barrier, one that compels us to consider not only what might have survived, but also how much of our planet's distant past has been irretrievably lost to Earth's dynamic and ever-changing surface. Current dating and analytical techniques, while remarkably advanced, face significant limitations when it comes to identifying and confirming ancient technological signatures, especially those originating from civilizations that predate human history. Radiometric dating methods, such as uranium lead or potassium argon, rely on measuring isotopic ratios within mineral matrices to establish age. Although these techniques are highly effective for dating rocks and fossils, their applicability diminishes when seeking evidence of technological activity embedded in geological substrates. For example, detecting traces of metals, synthetic materials, or other artifacts remains challenging because such signals can be subtle, chemically indistinct, or altered over immense timescales. Similarly, techniques like thermoluminescence or optically stimulated luminescence, which can date the last exposure of minerals to heat or light, are limited by their sensitivity thresholds and the potential for signal resetting through thermal events or environmental disturbances. This means that even if an ancient artifact or technological residue existed, subsequent geological processes might have erased or significantly altered the original signals, rendering them indistinguishable from natural mineral formations. Analytical methods such as spectroscopy, microscopy, and isotope analysis are powerful tools for detecting anomalies or synthetic signatures. However, their effectiveness is hampered by issues like contamination, low concentration of target elements, or the difficulty in distinguishing artificial signals from natural mineral inclusions. For example, identifying a faint trace of a metal alloy or synthetic composite embedded deep within ancient sediments requires extremely precise measurements, which may not be feasible given the degradation over millions of years. Moreover, the spatial resolution of many techniques limits the ability to pinpoint minute or highly localized technological signatures, especially when those signatures are dispersed, diluted, or chemically indistinct from natural materials. Advanced imaging methods, such as scanning electron microscopy or synchrotron radiation, offer higher resolution but are still constrained by the rarity of preserved samples and the potential for post-depositional alteration. Collectively, these limitations underscore a fundamental challenge. Our current suite of dating and analytical techniques may simply be insufficient to reliably detect or confirm evidence of ancient technological civilizations that existed long before humans. The combination of subtle signatures, natural degradation, and the constraints of our tools creates a formidable barrier to uncovering the archaeological footprints of such distant and potentially enigmatic societies. Natural, geological, and biological processes present formidable obstacles to uncovering evidence of ancient, pre-human civilizations. Over millions of years, the Earth's surface has been in a constant state of flux, with tectonic activity continually reshaping continents through processes like subduction, continental drift, and mountain building. These dynamic forces can subduct or bury remnants of ancient civilizations deep within the Earth's crust, effectively erasing any surface traces that might have once existed. For example, large-scale volcanic activity can cover archaeological sites in thick layers of ash and lava, while erosion from wind, water, and ice gradually wears away surface features, dispersing or obliterating physical evidence. Biological activity further complicates the preservation of ancient traces. Microbial decay, plant root intrusion, and bioturbation, organisms burrowing through sediments, can disturb or destroy archaeological signatures. Over geological timescales, organic materials such as wood, textiles, or even bone tend to decompose unless exceptionally well-preserved conditions like anoxic environments or rapid burial are present. Unfortunately, such ideal conditions are rare, and most evidence is either degraded beyond recognition or completely lost. Moreover, chemical processes, including mineralization and leaching, alter or dissolve potential markers of past civilizations. For instance, groundwater movement can leach out organic molecules or dissolve mineral deposits that might have preserved artifacts or structures. Over millions of years, chemical weathering can render any remaining evidence indistinct or indistinguishable from natural mineral formations. The Earth's sedimentary record, which could provide clues to ancient civilizations, is itself a patchwork of incomplete and sometimes biased deposits. Sediments are often eroded, reworked, or buried unevenly, making it unlikely that any evidence of advanced civilizations, if they existed, would be neatly preserved in a continuous, accessible record. Consequently, the natural processes of geology and biology act as a relentless filter, erasing or obscuring potential signs of ancient, non-human civilizations and creating profound challenges for scientists attempting to detect such elusive traces. Several biases and assumptions can significantly hinder scientific inquiry into the Silurian hypothesis, potentially limiting objectivity and the scope of investigation. One primary bias is anthropocentrism, the tendency to view human civilization as the pinnacle or exclusive example of advanced life, which can inadvertently lead researchers to dismiss or overlook signs of ancient non-human civilizations. This perspective may cause scientists to interpret geological or biological anomalies solely through a human-centric lens, thereby constraining the detection of evidence that does not fit conventional expectations. Another assumption pertains to the perceived rarity or uniqueness of intelligent life. Many scientific models presuppose that complex, technologically capable civilizations are improbable or transient phenomena, which can discourage the search for subtle or indirect indicators of past civilizations. This bias might also influence funding priorities, steering resources away from unconventional or interdisciplinary approaches that could uncover more nuanced evidence. Furthermore, confirmation bias plays a critical role. Researchers may unconsciously favor interpretations that align with existing scientific paradigms, thereby dismissing anomalies or alternative explanations that could support the hypothesis. Additionally, methodological limitations and assumptions about the geologic record itself introduce biases. For instance, the belief that Earth's stratigraphic layers are sufficiently detailed and preserved to reveal ancient civilizations may overlook the dynamic nature of geological processes, erosion, tectonic activity, and sedimentation that can obscure or erase such evidence. There is also an implicit assumption that any technological traces would be easily detectable with current methods, ignoring the possibility that ancient technologies might have been different or less durable, rendering their signatures difficult to identify. Cognitive biases rooted in cultural and societal norms can further influence inquiry. Prevailing narratives about Earth's history tend to favor gradual, naturalistic explanations, which can diminish openness to revolutionary ideas like the existence of ancient, advanced civilizations predating humans. Collectively, these biases and assumptions create mental barriers that can hinder open-minded exploration and the development of innovative, investigative methods necessary to rigorously test the Silurian hypothesis. Recognizing and addressing these cognitive and methodological biases is crucial for fostering a more objective, comprehensive scientific pursuit of this intriguing possibility. Interdisciplinary collaboration is essential for surmounting the complex challenges involved in testing the Silurian hypothesis. Given that the hypothesis spans multiple scientific domains, geology, paleontology, archaeology, climatology, and even astrophysics, integrating expertise from these fields fosters a more comprehensive approach to uncovering evidence of ancient, pre-human civilizations. Such collaboration encourages the synthesis of diverse methodologies, datasets, and theoretical frameworks, which collectively enhance our capacity to interpret subtle signals buried within the Earth's deep history. For instance, geologists and paleontologists can work together to refine stratigraphic analyses and identify anomalous layers that may indicate prior technological activity or ecological disruptions. Archaeologists, with their expertise in artifact detection and site excavation, can contribute insights into potential hidden or eroded remnants of ancient structures, if any exist, while climatologists can model potential environmental changes that could obscure or preserve such evidence. Similarly, astrophysicists can analyze extraterrestrial influences, like asteroid impacts, that might coincide with periods of civilization, emergence, or collapse, providing context beyond earthbound data. This cross-disciplinary approach also fosters the development of novel analytical techniques. For example, advances in isotope analysis, remote sensing, and high-resolution imaging often emerge from collaborations across scientific borders. These tools can reveal faint chemical signatures or structural anomalies indicative of technological activity long after the civilizations themselves have vanished. Moreover, interdisciplinary dialogue encourages critical reassessment of assumptions, such as the time frame of geological processes or the stability of certain environmental markers, helping to minimize biases that might hinder detection efforts. Such collective efforts promote a more holistic understanding of Earth's history, increasing the likelihood of identifying subtle or indirect evidence of ancient civilizations. They also facilitate the design of integrated research projects and large-scale surveys capable of addressing the multifaceted nature of the problem. Ultimately, the synergy of diverse scientific perspectives not only broadens our investigative toolkit, but also enhances the robustness of interpretations, guiding us closer to uncovering the truth behind the Silurian hypothesis, and, perhaps, rewriting our understanding of human history itself. This collaborative foundation naturally leads us to consider how technological innovation can further expand our detection capabilities, pushing the boundaries of what we can observe and interpret in the quest for ancient civilizations. Technological innovation is central to expanding our capacity to detect and interpret evidence of ancient civilizations, especially those predating humans. Over the decades, advancements in analytical techniques have revolutionized our ability to scrutinize Earth's geological and biological records, allowing us to uncover subtle signatures that might otherwise remain hidden. For example, high-precision radiometric dating methods, such as uranium lead and argon-argon dating, have refined our timeline of Earth's history, enabling us to identify anomalies that could suggest extraordinary activity or disruptions caused by ancient technological civilizations. Moreover, developments in geochemical analysis, such as isotope ratio measurements, have opened new avenues for detecting artificial signatures. The presence of anomalous isotopic ratios or synthetic elements, like technetium or certain heavy metals, could serve as indirect markers of technological activity. These tools enhance our sensitivity to trace evidence of industrial processes or energy utilization that might have occurred millions of years ago. Similarly, advances in sediment analysis, including scanning for microfossils or nanostructures, help us recognize evidence of technologically influenced environments such as nanoscale artifacts or unusual mineral formations resulting from artificial manipulation. The rise of remote sensing technologies, like satellite imagery and deep Earth geophysical surveys, further broadens our detection horizon. These tools enable us to identify large-scale anomalies, buried structures, unnatural alignments, or disrupted stratigraphy that may indicate the presence of ancient constructed features. As sensor resolution improves, coupled with machine learning algorithms capable of detecting subtle patterns, our chances of recognizing signs of ancient civilization increase exponentially. Additionally, interdisciplinary approaches integrating paleontology, geology, archaeology, and even astrobiology foster more comprehensive searches. For instance, analyzing extraterrestrial influxes of materials or cosmic ray-induced isotopic changes might reveal indirect evidence of past technological activity. As our technological toolkit advances, so does our capacity to interpret complex signals, transforming the way we approach the profound question of whether humans are truly the first or the sole technological civilization on Earth. In essence, technological innovation continuously pushes the boundaries of what we can detect, interpret, and ultimately understand about Earth's deep past. Yet, this progress also prompts us to consider the limitations and potential biases embedded within our methods, an inquiry that naturally leads into questions about the epistemological limits of our knowledge. The pursuit of understanding Earth's deep past confronts not only scientific and technological hurdles, but also profound philosophical and epistemological limitations. At its core, epistemology, our study of knowledge, raises fundamental questions about what we can truly know and how reliably we can interpret the ancient signals embedded within geological records. These limitations stem from the inherent nature of the fossil record, which is fragmentary, biased, and subject to the transformative forces of Earth's dynamic processes. One major philosophical challenge lies in the problem of inference. Much of what we deduce about ancient life, especially civilizations that predate human history, relies on indirect evidence. For example, identifying traces of a hypothetical pre-human civilization from millions of years ago involves interpreting geological anomalies, isotopic signatures, or microfossil evidence. However, these indicators can often be ambiguous, overlapping with natural geological phenomena. This raises the question of whether our current scientific frameworks possess the capacity to distinguish between truly artificial artifacts and natural formations, an epistemological boundary rooted in the limits of observation and interpretation. Furthermore, the deep past is shrouded by what some philosophers term a fundamental epistemic horizon. As we delve further back in time, our ability to acquire definitive knowledge diminishes exponentially. The erosion, tectonic activity, and sedimentation continually erase or obscure potential evidence, creating a natural barrier akin to a cosmic horizon but on a geological scale. This means certain truths about Earth's earliest epochs might forever lie beyond human reach, not merely due to technological constraints, but because of the very nature of time and matter. Additionally, our scientific paradigms are shaped by current knowledge and technological capabilities, leading to a form of epistemic modesty. As new methods emerge, such as advanced isotope analysis or deep Earth imaging, we may revise or even overturn long-held assumptions. Yet, the possibility remains that some aspects of Earth's deep history are inherently unknowable, constrained by the limits of human cognition and observation. In essence, these philosophical and epistemological boundaries do not diminish our curiosity, but serve as a reminder of humility. They shape our understanding of what is possible to know about Earth's ancient past, prompting ongoing reflection on how evidence is interpreted and cautioning us against overconfidence in conclusions about civilizations long vanished from the geological record. The search for evidence of ancient civilizations beyond human history inevitably raises profound ethical questions, touching on issues of scientific integrity, cultural sensitivity, and societal impact. As researchers delve into geological and fossil records in pursuit of these hidden chapters of Earth's past, they must confront the moral responsibilities associated with their discoveries and interpretations. One primary concern involves the potential for misinterpretation and the consequences of prematurely labeling ambiguous findings as evidence of intelligent life. Such misclassifications could lead to misinformation, influencing public perception and scientific discourse in ways that undermine credibility and trust. Ensuring rigorous verification and transparent methodologies is essential, yet the very act of revealing tentative evidence carries risks of sensationalism or unwarranted speculation. Furthermore, discovering evidence of pre-human civilizations could challenge deeply held cultural and religious narratives. For some societies, such findings might threaten core beliefs about humanity's unique place in history, provoking resistance or denial. Conversely, for others, these revelations could inspire a re-evaluation of human origins, fostering humility and a broader sense of connection with Earth's distant past. Respecting diverse cultural perspectives becomes paramount, especially when handling artifacts or symbols that might be interpreted differently across traditions. Another layer of ethical complexity pertains to the preservation and stewardship of ancient sites and artifacts. If such evidence is found, questions arise about who has the right to access, study, or display these discoveries. There is a delicate balance between advancing scientific knowledge and respecting the cultural or spiritual significance that certain sites or objects may hold for indigenous or local communities. Finally, there is the issue of potential exploitation. The allure of uncovering lost civilizations could lead to the looting of sites or commercialization of artifacts, undermining their historical value and disrespecting the cultures associated with them. Establishing clear ethical guidelines and international cooperation is crucial to prevent such abuses. In sum, the quest to uncover ancient, possibly pre-human civilizations is fraught with ethical challenges that demand careful consideration. Responsible research must prioritize scientific integrity, cultural respect, and the preservation of humanity's shared heritage, ensuring that the pursuit of knowledge enriches rather than endangers our collective understanding of Earth's profound history. The potential discovery of pre-human civilizations would profoundly reshape human identity and cultural narratives, prompting a re-evaluation of our place within the broader tapestry of planetary history. For centuries, human self-perception has been centered around the idea of being the pinnacle or unique product of evolution. If evidence emerged indicating that intelligent life or technologically advanced societies existed long before humanity, this would challenge notions of human exceptionalism and elevate our understanding of life's resilience and continuity. Such a revelation might inspire a sense of humility, emphasizing that humanity is part of a much larger, possibly cyclic or layered, evolutionary story. Culturally, the acknowledgement of ancient civilizations predating humans could foster a paradigm shift in mythology, religion, and philosophical outlooks. Mythologies might be reinterpreted to incorporate echoes of forgotten worlds, and religious narratives emphasizing divine creation might be complemented by stories of cosmic or planetary renewal cycles. This broader perspective could also elevate the importance of stewardship, recognizing that human civilization is but a chapter in an ongoing saga of planetary life rather than its starting point. Furthermore, the idea of ancient, possibly technologically capable societies existing long before humans could inspire a reassessment of our technological and scientific potential. It might prompt questions about the rise and fall of civilizations, resilience, and the sustainability of technological advancement. Such insights could influence future strategies for societal development, emphasizing humility and caution in technological pursuits. On a psychological level, discovering ancient civilizations could deepen our appreciation for diversity in intelligence and cultural expression, broadening our understanding of what constitutes civilization and progress. It might also challenge ethnocentric views, encouraging a more inclusive perspective that recognizes the universe's capacity for complexity across different eras and environments. As we grapple with these profound implications, a critical question emerges. Should we prioritize preservation of potential sites and artifacts of these ancient civilizations, safeguarding their mysteries for future study, or should we pursue active exploration to uncover their secrets and understand their history? This dilemma underscores the importance of balancing respect for the past with the curiosity that drives scientific discovery, ensuring that our pursuit of knowledge remains ethically grounded and mindful of the broader implications for human identity and cultural narratives. When investigating ancient sites and artifacts, a fundamental debate arises. Should we prioritize preservation or exploration? Both approaches carry significant weight, especially within the context of potential discoveries that may challenge our understanding of history and the longevity of civilizations. Exploration drives the quest to uncover new evidence, pushing the boundaries of scientific knowledge. By actively excavating and analyzing sites, whether deep beneath the ocean, within ice cores, or across terrestrial landscapes, we can identify anomalies that may suggest the presence of ancient, possibly pre-human, civilizations. Advanced techniques like remote sensing, high-resolution imaging, and geochemical analyses enable us to detect subtle signs that might otherwise be overlooked. These efforts can refine our understanding of Earth's history, revealing complex interactions between natural processes and potential technological artifacts. However, exploration carries inherent risks. In its pursuit, there is a danger of disturbing fragile sites, destroying context that is crucial for accurate interpretation. Uncontrolled excavations may lead to the misinterpretation of natural formations, such as mineral deposits or geological anomalies, as artifacts of ancient technology or civilizations. The temptation to sensationalize discoveries can cloud scientific objectivity, especially when preliminary findings are misrepresented or overhyped, leading to misconceptions about humanity's history. Conversely, prioritizing preservation emphasizes the ethical responsibility to protect sites from damage and the scientific integrity of remaining undisturbed. Preserving sites ensures that future technologies and methodologies can further analyze evidence with greater precision, and that the context of artifacts remains intact for accurate interpretation. It also guards against the risks of premature conclusions that can distort public understanding or fuel pseudoscientific claims. Ultimately, a balanced approach is essential. While exploration is vital to expand our knowledge, it must be conducted with rigorous scientific standards and respect for the site's integrity. Preservation safeguards the context necessary for meaningful interpretation, preventing the pitfalls of misinterpretation and sensationalism that could arise from hasty or reckless investigation. Navigating this balance ensures that our pursuit of knowledge remains both responsible and scientifically sound, safeguarding the integrity of our understanding of Earth's ancient history. Misinterpreting or sensationalizing evidence related to ancient civilizations poses significant risks that extend beyond scientific inaccuracies to societal and cultural repercussions. At the core, such misinterpretations often stem from confirmation bias, selectively emphasizing ambiguous data to support preconceived notions, leading to distorted narratives that can mislead both the scientific community and the public. When fragile geological or archaeological signals are overstated, it can create false paradigms, diluting the integrity of scientific inquiry and diverting resources away from more grounded research. Sensationalism amplifies these risks by framing tentative findings as definitive proof of advanced ancient civilizations, which can generate unwarranted media hype. This not only fosters misconceptions, but also undermines public trust in scientific institutions when subsequent evidence fails to uphold exaggerated claims. Such episodes risk fueling pseudoscientific theories and conspiracy narratives, further polarizing discourse around human history and prehistory. Moreover, misinterpretation can have cultural and political consequences. Claims of discovering ancient advanced civilizations, especially if associated with specific geographic regions or cultural groups, may inadvertently reinforce stereotypes or ignite nationalist sentiments. Conversely, dismissing evidence due to cultural or religious biases can hinder genuine scientific progress by creating intellectual dogmas that resist challenging new ideas. For example, some religious perspectives might view the hypothesis as conflicting with traditional creation narratives, leading to outright rejection or suppression of evidence that seems to undermine deeply held beliefs. The tendency to sensationalize also risks trivializing genuine discoveries, reducing complex scientific phenomena to sensational stories that ignore nuance. This can diminish public understanding of the scientific process, fostering skepticism rather than appreciation. When evidence is misrepresented, the line between credible science and entertainment blurs, complicating efforts to communicate the importance of rigorous methods and cautious interpretation. Ultimately, the dangers of misinterpretation and sensationalism highlight the need for meticulous analysis, peer review, and responsible dissemination. Recognizing the cultural and societal sensitivities intertwined with these discoveries is vital to fostering an informed, open-minded dialogue, one that respects diverse perspectives while safeguarding scientific integrity. Cultural and religious perspectives profoundly shape how societies interpret extraordinary scientific hypotheses, including the possibility of ancient, pre-human civilizations. When evidence, be it anomalous geological formations, microfossils, or unconventional artifacts, suggests a history beyond human origins, entrenched worldviews often influence whether such ideas are embraced or dismissed. In many cultures, religious doctrines emphasize human uniqueness or divine creation, fostering skepticism toward hypotheses that challenge these narratives. For example, traditional Judeo-Christian perspectives may interpret geological anomalies or fossil anomalies as divine signs or deliberate designs, resisting their reinterpretation as evidence of ancient civilizations. Conversely, some indigenous worldviews may interpret geological features or mysterious artifacts as remnants of ancestral spirits or ancient wisdom, opening pathways for acceptance of the idea that humanity shares its planet with other intelligent beings from deep time. Cultural narratives also influence scientific discourse and public reception. Societies with a history of scientific skepticism or authoritarian control over knowledge may dismiss unconventional hypotheses to preserve ideological cohesion. In contrast, cultures with a tradition of mythic storytelling that acknowledges ancient beings or lost civilizations can be more receptive, framing scientific findings within familiar spiritual or philosophical contexts. Religious and cultural frameworks can also impact funding, research priorities, and the communication strategies employed by scientists. When findings appear to threaten core beliefs, there may be social or institutional resistance, which can hinder open inquiry or lead to the suppression of controversial evidence. Conversely, communities that view scientific exploration as complementary to their spiritual worldview may foster more open dialogue and curiosity. Ultimately, recognizing the influence of cultural and religious perspectives is crucial for scientists. It underscores the importance of sensitive, transparent communication that respects diverse worldviews while presenting evidence objectively. Engaging with cultural contexts can facilitate broader acceptance and understanding, especially when hypotheses about ancient civilizations challenge conventional narratives. As scientific inquiry advances, acknowledging these perspectives ensures a more inclusive, respectful dialogue, vital for expanding our collective understanding of human history and our place in the universe. Scientists bear a profound ethical responsibility in how they communicate discoveries related to ancient civilizations, especially when such findings challenge entrenched paradigms or have the potential to alter societal perceptions of history. As evidence of pre-human civilizations, whether derived from geological anomalies, microfossil analysis, or advanced detection techniques, becomes more compelling, Researchers must navigate the delicate balance between scientific integrity and public impact. Transparency is paramount. Scientists are obliged to present their findings with clarity, acknowledging uncertainties and methodological limitations to prevent misinterpretation. Overstating conclusions or overstressing the significance of ambiguous evidence risks fueling misconceptions, sensationalism, or unwarranted fears. Conversely, downplaying intriguing anomalies can hinder scientific progress and public curiosity. Striking this balance demands meticulous peer review, rigorous validation, and open dialogue within the scientific community before disseminating results broadly. Furthermore, scientists must consider the broader societal implications of their discoveries. Revealing evidence of an ancient, technologically advanced civilization could challenge deeply held cultural narratives, potentially undermining national identities or religious beliefs. As such, researchers have a duty to contextualize their findings within a framework that emphasizes scientific inquiry rather than sensationalism, fostering informed public discourse. There is also an ethical obligation to collaborate with historians, archaeologists, and cultural custodians to ensure that interpretations are respectful of diverse cultural heritages. When findings imply the existence of civilizations that predate known human history, it raises questions about who owns the narrative and how it should be integrated into existing cultural stories. Scientists must be sensitive to this, avoiding language that might incite cultural conflicts or territorial disputes. Finally, the dissemination of such groundbreaking information should aim to educate and inspire curiosity rather than incite fear or competition. Responsible communication involves clear, nuanced messaging that encourages ongoing investigation while respecting the cultural and societal ramifications that such discoveries could engender. As we delve deeper into Earth's ancient past, scientists must remain stewards of truth, integrity, and cultural sensitivity. The potential discovery of ancient civilizations predating human history inevitably raises complex questions about the management and protection of cultural heritage and territorial integrity. Such revelations could ignite disputes rooted in differing cultural, national, or scientific interests, especially if artifacts or sites are located within sovereign borders or are perceived as belonging to particular groups. Historically, the recognition and preservation of archaeological sites have often been entangled with issues of ownership, sovereignty, and cultural identity. Introducing evidence of an even older civilization could intensify these conflicts, challenging established narratives and prompting claims of cultural precedence. In the context of the Silurian Hypothesis, where signs of ancient technological activity might be embedded deep within geological layers, the stakes become even higher. The potential for discovering artifacts or structures that transcend traditional archaeological understanding could lead to disagreements over their interpretation. Some nations or groups might assert rights over certain sites, viewing them as integral to their cultural heritage, while others may advocate for open scientific investigation. Such disputes could be exacerbated if the sites are located on contested territories or if discoveries are perceived as threatening national identities or cultural sovereignty. Moreover, the commercial interests tied to resource extraction or tourism might complicate matters further. There could be economic incentives to either preserve or exploit these ancient sites, leading to conflicts between conservation efforts and development goals. Without clear international guidelines, disputes might escalate, risking damage to invaluable scientific and cultural resources. To navigate these potential conflicts, it is essential to consider frameworks that prioritize respect, collaboration, and transparency. Recognizing the importance of cultural heritage, many international conventions, like UNESCO's World Heritage Agreements, highlight the need for shared stewardship and responsible stewardship of significant discoveries. Establishing protocols that involve local communities, nations, and the global scientific community can foster trust and ensure that the pursuit of knowledge does not come at the cost of cultural or territorial integrity. As we venture into unveiling Earth's deep history, These ethical and diplomatic considerations become crucial to ensuring that exploration enriches humanity's collective understanding without sowing division. Ethical frameworks are essential in guiding the responsible pursuit of understanding Earth's deep history, particularly when investigating the tantalizing possibility of ancient civilizations predating humanity. Such exploration raises profound questions about our place in Earth's narrative and demands a cautious, reflective approach that balances scientific curiosity with moral responsibility. Foremost, transparency and integrity must underpin research efforts, ensuring that claims of discovering evidence of ancient technology or civilizations are rigorously vetted and free from sensationalism. This safeguards public trust and prevents the dissemination of misinformation that could distort scientific discourse. Moreover, adopting an interdisciplinary perspective is vital. Ethical frameworks should foster collaboration among geologists, archaeologists, paleontologists, ethicists, and indigenous communities to ensure that interpretations respect cultural sensitivities and environmental considerations. For instance, if certain geological features are interpreted as potential artifacts, researchers must consider the broader implications for cultural heritage and environmental stewardship. This holistic approach helps prevent potential misappropriations of findings and promotes a responsible stewardship of Earth's history. Another critical aspect involves weighing the potential impacts of discovery, scientifically, culturally, and socially. If evidence suggests that advanced civilizations existed long before humans, it could challenge entrenched paradigms and necessitate re-evaluations of human origins. Ethical research must therefore anticipate the societal ramifications of such findings, ensuring that interpretations are communicated responsibly and that claims are made cautiously to avoid undermining scientific credibility or inciting unwarranted speculation. Furthermore, fostering a mindset of humility and open-mindedness is crucial. Recognizing the limits of current technologies and methodologies encourages scientists to avoid overreach and to transparently communicate uncertainties. This ethical stance promotes integrity and invites a collaborative effort toward refining detection techniques and interpretations. In essence, ethical frameworks serve as a compass that ensures the exploration of Earth's deep past proceeds with respect, responsibility, and scientific integrity. As we venture into the uncharted territories of pre-human history, these guiding principles help balance our innate curiosity with the moral obligation to honor the complexity and significance of Earth's ancient narratives. This responsible approach not only advances scientific understanding, but also preserves the integrity of our collective pursuit of knowledge.